Welcome to night cosmos sleep. For most of human history, the moon was a distant world that could only be observed from the ground. Then, the first footprints appeared in its gray dust, proving that we could reach its surface. But more than half a century later, the goal is gradually beginning to change. Humanity no longer wants merely to fly to the moon, spend a few hours on the surface, and then return home. New plans are moving toward a far greater challenge. Building shelters, maintaining breathable air, finding sources of water, generating electricity, and allowing astronauts to live there for weeks or months at a time, perhaps even returning on a regular basis. The distance between visiting a place and making it habitable is far greater than we often imagine. The moon has no air to breathe, no flowing water, no global magnetic field to protect the human body, and no rescue team waiting nearby. Every drop of water, every breath of oxygen, and every source of light must either be transported there, recycled, or produced by systems that cannot be allowed to stop working. So will the coming decade truly mark the beginning of human life on the moon? Or are we only beginning to learn how to survive in a world that was never made for life? To find the answer, we must move through each small step, each experiment, and each boundary that has yet to be crossed. On the 10th of April 2026, a spacecraft capsule plunged into Earth's atmosphere. Inside were 4 people who had just traveled around the moon, seen regions of its surface that always face away from us, and ventured farther than any crew had in more than half a century. Yet, throughout the entire journey, no one stepped onto the gray dust below. When the capsule touched down in the ocean, the greatest question remained behind. Does reaching the moon mean we are ready to live there? During the final hours of Artemis II, the moon gradually receded behind Orion. The gray world that had once filled much of the view outside the windows slowly became a small object suspended in the darkness once again. Ahead of the spacecraft, Earth grew larger, covered in white clouds, blue oceans, and a thin atmosphere that was almost impossible to see. It was a place where humans did not have to manufacture the air they breathed, where water flowed without needing to be recycled, and where a broken piece of equipment did not immediately threaten their survival. Orion was returning home. Inside the capsule were Commander Reed Wiseman, pilot Victor Glover, NASA mission specialist Christina Koch, and Canadian Space Agency astronaut Jeremy Hansen. They had not set out to plant another flag on the moon. Artemis II was the first crewed flight of the Artemis program, designed to determine whether the SLS rocket, the Orion spacecraft, its life support systems, and crew procedures could all operate together during a journey around the moon. The flight began on April 1 and ended on the 10th of April 2026, lasting 9 days, 1 hour, and 32 minutes. During that time, Orion had to carry 4 astronauts beyond near-Earth space, deep into the darkness between 2 worlds, through the vicinity of the moon, and then safely back again. Every stage had been calculated with great care, because even a small change in direction or speed could have pushed the spacecraft away from its planned corridor home. As Orion approached Earth, there was no runway waiting below. The spacecraft had to enter the atmosphere at an angle precise enough to slow it down without creating forces or temperatures beyond safe limits. If the entry angle was too shallow, the capsule might not decelerate as expected and could continue skimming through the upper layers of the atmosphere. If it was too steep, the heat and the forces acting on the crew would rise rapidly within a very short time. Ahead of Orion, the air was almost non-existent at first, but as the spacecraft descended, increasingly dense gas molecules were compressed against its heat shield, creating an intensely hot region around the capsule. The protective material on the exterior had to burn away in a controlled manner, carrying heat away from the spacecraft. Meanwhile, the 4 astronauts remained seated inside a sealed cabin, where pressure, temperature, and air composition were continuously monitored by automated systems. Inside that capsule, every breath depended on machinery. Orion had to provide enough oxygen for the crew while removing the carbon dioxide they exhaled. The spacecraft also had to regulate humidity, circulate the air, and manage the heat produced by human bodies and onboard equipment. A small cabin could quickly become dangerously warm if the cooling system malfunctioned, while an unwanted gas could quietly accumulate if the filtration equipment stopped working properly. But Orion was not designed to be a completely self-sufficient world. Its systems served a mission of limited duration. with water, food, reserve oxygen, and other supplies calculated before the spacecraft ever left the ground. The crew knew approximately how long they would remain in space, when their trajectory would bring them home, and how many resources would be required for each day of the journey. Back on Earth, engineering teams continued to monitor the data, evaluate every change, and help resolve any problems that emerged. A lunar base would not have that same simplicity. It could not carry only enough water for a short visit and then return home before the supply began to run out. It would need to recover moisture from the air, process used water, and reduce the amount of material that had to be transported from Earth. Nor could it rely on a single system to keep the air breathable. It would need backup equipment, replacement parts, and ways for the crew to carry out repairs themselves when no engineering team could simply walk in from outside. A flight may end before a piece of equipment begins to deteriorate seriously. A base must continue operating through the 20th day, the 50th day, and perhaps the 100th. Pumps must keep moving water through pipes, fans must keep the air circulating, and filters must remove dust and contaminants for months at a time. Over time, very small problems can gradually accumulate until they begin to affect the entire system protecting human life. On a short mission, waste can be sealed away and stored until the flight is over. In a long-term habitat, every bag of trash takes up space, every dirty filter must be replaced, and every disposable item adds mass to the next resupply mission. Nothing truly disappears on the moon. Everything brought there must be used, recycled, repaired, stored, or eventually returned to Earth. Time also changes the way people evaluate the durability of equipment. A fan that runs reliably for 9 days has not yet proven that it can operate continuously for months in an environment filled with dust and extreme temperatures. A seal that keeps a spacecraft airtight during a single flight may not withstand hundreds of door openings and closings. A spacesuit that performs well during a few moonwalks may also begin to fail when sharp dust particles repeatedly cling to its joints, fabric layers, and protective visor. While Orion is always moving toward a carefully calculated point of return, a lunar base must remain in place and wait. It must endure periods when no spacecraft is nearby, maintain safe temperatures when sunlight is blocked by the surrounding terrain, and protect its occupants from radiation and severe environmental changes. On Earth, a minor failure can often be solved by calling for assistance. On the Moon, the crew must become its own repair team, medical staff, and emergency responders. For that reason, the success of Artemis II is a major step forward, but it is not proof that humanity is ready to build a home on the Moon. The mission confirmed that a new system could carry a crew around the Moon and return them safely to Earth. After Orion splashed down in the Pacific Ocean, engineers continued analyzing data from the spacecraft, the rocket, and every stage of the mission. Each result will be used to refine the designs and prepare for more complex missions. That information is important because Artemis is not beginning from nothing. More than half a century ago, the Apollo program placed 12 people on the surface of the Moon. Those missions proved that humans could leave Earth, land on another world, work on its surface, and return home. Apollo accomplished the goal of its era, and the fact that the astronauts did not remain there does not mean the program failed. The Apollo astronauts carried everything they needed for a limited stay. The lunar module served both as their landing vehicle and as a temporary shelter. They collected rock samples, deployed scientific instruments, examined the terrain, and left before the limits of electricity, water, oxygen, and supplies became impossible to manage. It was an expedition designed to arrive, complete its mission, and return, not to establish a permanent settlement. Their footprints still remain in the gray dust. The Moon has no rain to wash them away, and no wind to soften the outlines pressed into the surface. Those impressions may survive for a very long time, like small lines of writing recording the moment humanity first touched another world. But beside them, there are no functioning power lines, no heated living modules, and no vehicles waiting for the next crew. When the Apollo spacecraft left the surface, most human activity there ended as well. The instruments left behind gradually fell silent or continued making only a limited number of measurements. No system had been built to receive new astronauts many years later. Each mission had to begin almost entirely from the start, carrying its own vehicles, supplies, and temporary shelter. Artemis is being built around a different goal. The program is not simply intended to reach the moon one more time, but to gradually create the ability to return more often. Humans do not merely want to take another short walk across the surface. They also want to learn how to extend the amount of time they can work there. Instead of transporting everything from Earth on every journey, researchers want to determine whether lunar water, soil, and local conditions can support part of a long-term human presence. That goal makes Artemis more complicated in ways that are not always immediately visible. A single landing can be organized around one vehicle and one clearly defined mission. A lasting system requires many spacecraft, organizations, launches, and layers of infrastructure to work together. From the moment the crew leaves Earth until they step onto the surface, every vehicle must arrive at the right time and perform the role for which it was designed. Orion is responsible for carrying people away from Earth and bringing them home, but it was not designed to land on the lunar surface by itself. The crew will need another vehicle to travel from lunar orbit to the ground. Cargo, habitats, rovers, power equipment, and communication systems may arrive on separate flights. These components may be built by different organizations, but in the end, they must operate as parts of the same system. A connecting hatch must do more than have the correct dimensions. It must hold in the air, withstand the movement of two vehicles, and allow astronauts to pass through safely. Computers must be able to exchange data, electrical systems must be compatible, and spacesuits must work with the lander's airlock. Cargo must also be placed in the correct area so that robots or astronauts can reach it without making unnecessary and dangerous journeys. If one component falls behind schedule, the entire sequence of missions may have to change. If the lander has not passed enough tests, Orion may still be able to fly, but the crew will not yet be able to reach the surface. If the habitat is not ready, humans may land, but remain only briefly. If the power system is not durable enough, a base may function in sunlight, but fail to survive long periods of darkness. This is why one successful flight cannot answer every question about humanity's future on the moon. Artemis 2 tested one of the most important parts of the journey, carrying people beyond the familiar region around Earth, flying past the moon, and returning in a new spacecraft. But the lander, habitat, power grid, rovers, water extraction systems, and other surface equipment must still be tested through many separate stages. The schedules of future missions may continue to change. Vehicles built by different organizations must still prove that they can work together under real conditions. Many devices that appear complete inside laboratories on Earth have not yet endured lunar dust, vacuum, radiation, and temperature extremes for long enough. Between a promising design and a proven system, many test flights still remain. None of this diminishes the importance of Artemis 2. Instead, it shows that the return to the moon is being built more carefully. Rather than treating a landing as the final destination, each mission becomes preparation for the one that follows. Every piece of data collected from Orion can help improve future designs, and every minor problem discovered during flight may prevent a more serious failure when humans travel farther from Earth. During the final minutes of April 10, Orion's parachutes opened above the Pacific Ocean. The capsule slowed, descended gradually, and touched the water. Recovery ships were already waiting nearby, allowing their crews to reach the astronauts quickly. The air outside was breathable, the ocean surrounded the capsule, and beyond the horizon lay a world filled with hospitals, factories, roads, and millions of people capable of supporting them. The joy of their return was entirely deserved. The 4 astronauts had completed the first crewed flight around the moon in more than half a century. Orion had carried them through deep space and brought them safely home. A new door had opened, but on the other side still lay a world with no recovery teams, no ocean to land in, and no atmosphere waiting for humans when they stepped outside. The Apollo footprints still rest in the dust, while the first human home on the moon exists only in systems being designed, equipment being tested, and missions that have not yet left the launch pad. The return flight proved that humans could once again travel through the space surrounding the moon. But remaining there will require many steps more difficult than any single journey. Before anyone can step onto the moon, two spacecraft built by different organizations must first learn how to find each other in space. Two spacecraft are moving at thousands of kilometers per hour. From a distance, they are little more than 2 points of light crossing the blackness of space, one carrying humans, the other designed to someday bring them down to another world. To connect, they cannot stop in the emptiness and wait for each other to arrive. They must continue falling around Earth, slowly adjusting until their positions, directions, and movements become almost identical. This is the challenge at the heart of Artemis 3, the next crewed flight in the Artemis program. Under the plan NASA is still finalizing, the mission will take place in 2027, carrying 4 astronauts into low Earth orbit aboard Orion and the SLS rocket. Instead of continuing toward the moon, Orion will remain near Earth to conduct rendezvous and docking tests, with experimental versions of lunar landers being developed by SpaceX and Blue Origin. The data collected will support Artemis 4, the mission currently targeting a crewed landing near the moon's south pole in 2028. At first, remaining in Earth orbit after a mission that traveled around the moon may seem like a step backward. Artemis 2 carried humans beyond familiar space, while Artemis 3 will fly only above the oceans and continents of our own planet. But the greatest distance traveled is not always the most important measure of a mission. Sometimes the necessary step forward is to perform a complex maneuver in a place still close enough for mistakes to be identified, procedures to be corrected, and the crew to return safely if a system does not work as expected. Orion and the lander can be imagined as 2 trains moving along curved tracks around Earth. Neither can stop halfway, and neither can simply turn around whenever it chooses to search for the other. For their hatches to come together, they must arrive at the same location at almost exactly the same time, moving in the same direction at nearly the same speed. If one vehicle arrives only a few minutes early or travels along a slightly different orbit, the distance between them can quickly grow to tens or even hundreds of kilometers. In space, catching an object ahead does not always mean simply accelerating. A spacecraft may need to change its orbital altitude, follow a different arc, and then allow its natural motion to bring it closer to the target. This may seem contrary to our experience on the ground, where a faster car usually catches the vehicle ahead. But in orbit, every change in speed also changes the path around Earth, so each maneuver must be calculated in relation to both position and time. When the distance is still large, Orion can approach the target at a noticeable relative speed. But the closer it gets, the more slowly it must move. From several kilometers away, the 2 spacecraft close the distance in careful stages. From a few hundred meters, each adjustment becomes a brief thruster pulse. And during the final few meters, the approach must be so slow that it is almost impossible to see with the naked eye. A spacecraft racing around Earth may appear motionless outside the window of another, but only because both are moving in almost exactly the same way. This is what it truly means to remain still beside another object in space. The 2 vehicles do not actually stop moving. They continue racing around the planet at enormous speed while the distance between them remains nearly constant. If Orion moves only slightly faster, it will gradually pass the target. If it moves more slowly, the lander will begin to drift away. What matters is not the absolute speed of either spacecraft, but the very small difference between their motions. During Artemis 3, the experimental landers will serve as targets, while Orion will be the active vehicle making the approach. This arrangement was chosen because it resembles how future lunar missions are expected to operate. The lander will be launched first and wait in orbit, after which Orion will arrive carrying the crew and connect with it. Blue Origin is expected to launch its test vehicle first, allowing it to remain in orbit while its systems are checked. After that phase, SpaceX will launch an experimental version of Starship for a separate docking with Orion. The approach does not depend solely on astronauts looking through the windows. Orion uses sensors, navigation computers, and small control thrusters to determine the distance and direction of motion of the spacecraft ahead. On the ground, engineering teams also monitor data from both vehicles, comparing their predicted positions with their actual locations and preparing to stop the approach if anything appears unusual. The crew may allow automated systems to perform many of the maneuvers, but they must still understand what is happening and be ready to intervene when necessary. Even a small deviation may require the entire process to begin again. If Orion approaches too quickly, the two large structures could collide with enough force to damage the docking port or nearby equipment. If the spacecraft drifts to one side, the components designed to capture each other may no longer align correctly. In that case, Orion must retreat to a safe distance, determine the cause, and attempt another approach rather than trying to correct the error during the final few seconds. This slowness is not a sign of hesitation. It is part of staying safe. At a distance of only a few meters, every movement must be small enough to stop before it becomes dangerous. There are no brakes in the familiar sense, no road surface to create friction, and no air to gradually slow the motion. A brief burst from a thruster can cause the spacecraft to keep drifting until another force is applied in the opposite direction. When the two docking rings touch, the process is still not complete. Capture mechanisms must engage correctly, pull the vehicles together, and lock them into a single connected system. The joint must be strong enough to withstand the motion of both spacecraft, while layers of seals create an airtight passage between the two pressurized cabins. The crew cannot open the hatch immediately because they must first confirm that no air is escaping into the vacuum outside. On Earth, a small gap around a window may create nothing more than a faint draft. In space, an opening between a spacecraft cabin and the vacuum outside will continuously pull air away. A docking port is therefore more than a place where two metal structures touch. Once locked, it must become part of the cabin wall, holding pressure inside and forming a passage safe enough for people to cross. The two vehicles must also be compatible in many ways that cannot be seen from the outside. They need to exchange data so their computers can understand each other's condition, including pressure, temperature, electrical power, and the motion of the combined spacecraft. The software must correctly interpret every signal being transmitted, while mission controllers must know which system is in control. If both spacecraft attempt to adjust their orientation according to different commands, the movement of the combined structure may become difficult to predict. The dockings with Blue Moon and Starship will not be entirely alike. Orion is expected to connect to the side of the Blue Moon test vehicle near its crew compartment and then dock nose to nose with Starship. When connected to Blue Moon, Orion's systems are expected to control the movement of the combined spacecraft. During the Starship docking phase, the SpaceX vehicle will take on that role. These differences will allow engineers to observe how Orion operates with two designs that have different sizes, shapes, and control systems. The crew must also determine whether humans can actually use the passage created by the docking system. Under the current plan, as many as 2 astronauts may open the hatch and enter the Blue Moon test vehicle to evaluate its interior space, equipment layout, and the ease of moving between the two spacecraft. They will not enter Starship during this mission, but the docking will still allow engineers to examine how the two vehicles interact, exchange information, and move once joined into a single large structure. Moving from Orion into a lunar lander may sound as simple as walking through a doorway, but in near weightlessness, the body does not remain naturally planted on the floor. Astronauts must use handrails to control their movement, avoid striking control panels, and carry equipment through a relatively narrow passage. A push slightly stronger than intended could send them drifting toward the opposite side of the cabin. For that reason, the position of the handrails, the width of the hatch, and the interior arrangement must all be tested by the people who will actually use them. On future landing missions, the process will become even more complicated because the astronauts will need to bring suits designed for the lunar surface. These suits are larger and more rigid than ordinary clothing, with their own life support systems and joints that must be protected. The docking passage and the interior of the lander must be wide enough for a suited astronaut to turn, move equipment, and prepare for the next stage of the mission. NASA is also using Artemis 3 to evaluate how future lunar spacesuits will interact with the lander before astronauts must perform those movements far from Earth. But Artemis 3 is not only a test between machines, it is also a test of the teams operating them. Orion belongs to NASA's system, while the landers are being developed by SpaceX and Blue Origin, each with its own software, control centers, and procedures. During every phase, everyone must know who has the authority to send commands, which data must be shared, and who is responsible when a warning appears. A mission like this requires several launches to occur within a relatively short period. Blue Origin's test vehicle must reach orbit and complete its checks before Orion approaches. SpaceX must also place Starship into the correct orbit for its part of the test. On the ground, launch sites, communication networks, and control centers must operate as parts of a single campaign, even though they are located in different places and managed by different organizations. If one vehicle is delayed, the entire sequence may have to change. If a test spacecraft fails to reach the correct orbit, Orion cannot simply fly anywhere it chooses to search for it. If a communication system becomes unstable, the docking may need to be postponed, even when the two vehicles are already relatively close. Situations like these allow NASA to test not only the hardware, but also the ability to revise a plan when many systems depend on one another. This is not a ceremonial demonstration intended merely to produce images of two spacecraft joined above Earth. Every step recreates part of a future lunar landing. When Orion arrives in lunar orbit, the lander will already be waiting there. The crew must find it, approach it, dock, transfer people and equipment, and then separate before descending to the surface. After completing their work on the Moon, the lander must carry the astronauts back into orbit. Once again, it must locate the waiting Orion, close the distance, and dock precisely. Only then can the crew return to Orion for the journey home. The entire mission therefore depends not on a single rendezvous, but on the ability to repeat the maneuver at moments when every minute of delay consumes additional electricity, water, and oxygen. Near Earth, a serious problem may still allow Orion to return within a relatively short time. Ground teams have many opportunities to communicate, and recovery forces can prepare to meet the capsule after it lands in the ocean. Around the Moon, humans will not have the same margin of safety. A docking seal that does not close properly, a misaligned sensor, or software that fails to exchange data correctly could prevent the crew from entering the lander or returning to Orion after leaving the surface. For that reason, if a maneuver is still difficult while Earth fills the view below the windows, it will be far more dangerous when the home planet has become only a small sphere in the distance. Artemis 3 places the test in Earth orbit not because the goal has become less ambitious, but because the mission is dividing a complicated problem into steps that can be examined one at a time. Mistakes discovered close to home will not have to appear for the first time when humans are already too far away to return easily. Not every detail of Artemis 3 has been finalized. The mission duration, the final order of some activities, and the scope of the tests may continue to change as Orion, Blue Moon, and Starship are built and evaluated. The progress of uncrewed flights will also affect the readiness of each system. NASA describes the current plan as a configuration that is still being refined, meaning some elements may be adjusted before launch. That uncertainty does not make the mission any less necessary. Instead, it reflects the nature of a program in which several new vehicles are being developed at the same time. Only after each spacecraft has demonstrated its capabilities can engineers determine exactly how they should work together. A plan adjusted according to reliable test results is more trustworthy than a schedule kept unchanged merely to create the impression that everything is moving forward. Throughout Artemis 3, Earth will remain close. With every orbit, the astronauts will be able to see blue oceans, bands of white clouds, and the glow of the atmosphere below. But inside the spacecraft, they will be practicing a sequence of operations meant for a place nearly 400,000 kilometers away. Every slow approach, every locked docking hatch, and every passage between two vehicles will prepare them for the moment when there is no longer a large planet directly beneath them. Not every step forward leaves a footprint on another world. Sometimes the most important advance is simply two hatches opening in space, an astronaut passing through, and then returning safely. It is the moment when vehicles designed separately begin operating as one system, and when the journey down to the Moon slowly changes from a drawing into a series of proven actions. Once the two vehicles have learned how to find each other, the next challenge will no longer lie in Earth orbit. It will be waiting in a landscape where sunlight creates deep shadows, rocks may remain hidden beneath uneven terrain, and a spacecraft cannot open parachutes to slow its descent. It is a place with no atmosphere to soften the fall. At the Moon's south pole, the sun never climbs high into the sky. Its light travels almost horizontally across the surface, striking ridgelines and casting long bands of darkness over the gray soil. Even a small rock can hide the ground behind it, while a deep crater may remain in shadow for so long that water ice can survive there for billions of years. This is where humans now hope to land. Under the current plan, Artemis 4 is aiming for a crewed landing near the lunar South Pole in early 2028. 2 members of the crew are expected to leave Orion aboard a commercial lander, descend to the surface, and work there for about a week before returning to orbit. But 2028 remains a target rather than a guaranteed landing date, because the vehicle selected for the mission must still complete many stages of testing before it can carry humans. The South Pole was not chosen because it is the easiest place to reach. On the contrary, its terrain is far more rugged than the relatively flat equatorial regions visited during Apollo. Craters lie close together, slopes change abruptly, and visibility is often limited by nearby horizons. Yet those same harsh conditions create opportunities that may become important for both science and a long-term human presence. Some elevated areas and ridges near the pole may receive sunlight for longer periods than the lower ground around them, offering opportunities to use solar energy and keep equipment within more manageable temperature ranges. Not far away, craters that never receive direct sunlight may preserve water ice and other volatile materials. The short distance between areas with favorable illumination and dark regions containing resources gives the South Pole enormous potential, but it also means that operations must take place across very different kinds of terrain. The soil and rocks there may also preserve evidence from the earliest history of the solar system. They have not been disturbed by wind, rain, or intense geological activity as they would be on Earth. So every collected sample may reveal part of a story billions of years old. For scientists, the South Pole is not only a place to search for water, it is also an ancient archive that may help humanity understand how the moon formed and how past impacts shaped the planets. But before any rock sample can be lifted from the ground, the spacecraft must land safely. On Earth, a returning capsule can use the atmosphere to slow down and then deploy parachutes before reaching land or sea. The moon has no significant atmosphere to perform that task. There is not enough drag to reduce the speed of the fall, and there is no air to hold a parachute open above the vehicle. The lander must use its engines to control nearly the entire descent. From orbit, the vehicle begins lowering its altitude, adjusting its direction, and gradually removing the speed that keeps it moving around the moon. Its engines must continue operating until the final seconds before the landing legs touch the ground. If the thrust is too weak, the vehicle will descend faster than expected. If it is too strong or uneven, the lander may tilt, drift away from the safe zone, or consume additional fuel, correcting its path. A large lander cannot simply choose any patch of ground that appears reasonably flat. The surface must be stable enough that the landing legs will not sink deeply or come to rest at sharply different heights. There must be no large rock underneath that could strike the engines or the body of the spacecraft. But even small craters can become dangerous if a landing leg settles directly into one. The guidance system must observe the terrain, compare it with onboard maps, and make decisions while the vehicle continues descending. At the South Pole, that task becomes more difficult because the light always arrives from a very low angle. The sun remains close to the horizon, causing shadows to extend many times farther than the objects that cast them. Ground facing the sun may appear intensely bright, while a nearby area can be so dark that sensors and human eyes struggle to recognize its details. An illuminated boulder may stand out clearly, while the crater behind it nearly disappears into shadow. Low-angle light does more than make the scene appear darker. It also makes height and slope more difficult to judge. On Earth, the human eye often relies on color, atmospheric haze, shadows, and familiar objects to estimate distance. On the moon, the sky is always black, there is no atmosphere to make distant objects fade, and the landscape is composed almost entirely of shades of gray. A gentle slope may appear flat until the observer moves much closer. Elevation maps created by orbiting spacecraft help engineers identify more suitable regions, but they cannot completely replace observation during the final seconds of descent. Rocks smaller than the resolution of orbital data may still be scattered across the landing zone. Shadows also shift as the sun moves around the horizon, meaning a safe landing site can appear very different several days later. The exact lighting conditions must therefore be considered when choosing the time of touchdown. NASA has identified several candidate regions near the South Pole, but the final site will depend on the capabilities of the lander, the launch window, lighting conditions, and the scientific goals of the mission. A vehicle capable of more precise landings may be able to reach a smaller or rougher area, while another design may require a wider and flatter landing zone. Because it is still uncertain which lander will be ready first, the final choice must wait for additional test data. As the spacecraft approaches the ground, another problem begins to emerge. The hot exhaust from its engines strikes the loose soil directly beneath the vehicle because there is no thick atmosphere to disperse the flow in the familiar way. The ground may erode, while dust and small fragments of rock are blown sideways at high speed. These particles can obscure the view of sensors, strike the landing legs, or travel toward equipment already placed on the surface. The engine exhaust may also alter the very ground on which the spacecraft is preparing to land. If the soil beneath it is excavated unevenly, one landing leg may come to rest on a different kind of surface from the others. With vehicles larger than the Apollo landers, more powerful engines may disturb a wider area and send material much farther away. Engineers must therefore understand not only how the spacecraft slows down, but also how its exhaust interacts with a surface made of dust, small rocks, and layers of soil with different levels of compaction. Robotic missions are helping gather the data needed to understand this problem. Camera systems mounted near a lander's feet can observe how the soil changes during descent, allowing researchers to reconstruct the shape of the surface before and after it is disturbed by the engines. Each uncrewed landing provides more information about how much dust is lifted, how far the particles travel, and what risks they pose to nearby equipment. These findings will help guide the design of both crewed landers and future landing sites. Precise landing is therefore necessary not only to protect a single spacecraft. It also determines whether multiple vehicles can eventually form a functioning base. Cargo, living modules, power systems, and rovers must be delivered close enough for people to connect and use them. But if spacecraft land too near one another, the exhaust from a later arrival could cover existing equipment in dust or send fragments of rock flying toward assets already on the surface. Future landing zones may need to be placed at a safe distance from habitats and sensitive equipment, while remaining connected to them by routes surveyed in advance. That distance cannot be too great, because every cargo journey across the moon consumes time, electricity, and human effort. But it cannot be too small either. If a landing could damage solar panels, observation windows, radiators, or pipelines installed earlier. The construction of a lunar base begins with the way each spacecraft chooses where to touch down. Once the engines shut off, the surface becomes silent again. There is no roar traveling through the air, no wind carrying the dust away, and no clouds slowly fading from the sky. Particles thrown upward fall back along curved paths under the moon's weak gravity, while some may cling to the landing legs, sensors, and nearby surfaces. Outside the windows, sunlight continues to stretch along the horizon, leaving deep darkness immediately beside the ground it illuminates. For the crew, touchdown is not a moment when they can immediately open the hatch and step outside. They must confirm that the lander is stable and check the pressure, electrical power, and every system required for the return to orbit. The spacecraft is not only the vehicle that brought them down, it is also their only way off the surface, so every sign of trouble must be examined before the astronauts begin their first moonwalk. When the final hatch opens, the human body still does not come into direct contact with the lunar environment. Between the astronaut and the vacuum is a suit designed like a miniature spacecraft. It must maintain pressure, supply oxygen, remove carbon dioxide, regulate temperature, and protect the wearer from dust and outside hazards. The suit must be sealed tightly enough to keep life from escaping, yet flexible enough for the astronaut to bend down, use tools, and move across sloping terrain. The moon's gravity, only 1/6 as strong as Earth's, makes bodies and equipment lighter, but it does not make the work simple. The suit still has mass, and once it begins moving, it cannot be stopped as easily as ordinary clothing. Every step must be adjusted to the ground. While maintaining balance becomes more difficult, because the wearer cannot clearly see their feet or bend their body in familiar ways. A small rock hidden in shadow may be enough to interrupt an astronaut's rhythm and cause a fall. A distance of only a few hundred meters on the Moon may therefore require far more time than the same distance on Earth. Astronauts must avoid slopes that increase the risk of slipping, areas of unstable soil, and routes hidden from the view of their crewmates. They must also continuously monitor their oxygen supply, electrical power, suit temperature, and the amount of time needed to return to the lander. Every excursion must preserve a reserve for the possibility that the journey back takes longer than expected. The terrain can also interrupt direct communication. A ridge or crater wall between an astronaut and the lander may block the signal, especially when communication equipment depends on a relatively clear line of sight. Candidate landing regions must take visibility toward Earth into account, but when astronauts descend into low areas or approach deep craters, they may still need relay stations or supporting satellites. A route with great scientific value may not be the easiest one along which to maintain contact. Each of the early missions will have to balance exploration with safety. Permanently shadowed regions may contain water ice, but they are also extremely cold, receive no sunlight for directly charging batteries, and are difficult to navigate. Elevated areas with better illumination are more favorable for power generation, but may lie far from important scientific targets. Humans cannot simply land where the greatest concentration of resources is found. They must choose a location safe enough to live, close enough to reach their objectives, and suitable enough for the spacecraft to depart again. During the first hours of surface work, astronauts may deploy instruments, collect samples, and examine details that orbital cameras cannot see. But every time they kneel or press a tool into the ground, dust clings to their gloves, knees, and the lower portions of their suits. These particles have not been rounded by water or wind like sand on Earth. They are sharp, adhesive, and capable of wearing down fabric, joints, pressure, seals, and optical surfaces. When astronauts return to the lander, the dust does not remain outside. It follows their suits to the hatch, becomes trapped in folds, and clings to the tools they bring inside. Apollo astronauts found that lunar dust scratched surfaces, interfered with mechanical equipment, and caused irritation when it entered the living space. During a mission lasting about a week, dust control is already important. For a base operating for months, it becomes a problem that must be managed every day. The landing, therefore, does not end with the image of a flag standing against the horizon. It ends when an astronaut returns to the hatch, looks down at their boots, and realizes that gray dust has settled over nearly everything. Outside, the sun remains low, dark shadows continue sliding across the terrain, and the small spacecraft is the only place preserving breathable air, safe temperatures, and a path home. Even after a perfect landing, the Moon has not yet become a place to live. Humans have only delivered a temporary room to the surface and closed the door to keep the outside world from entering. The next step is to create a shelter capable of protecting life for longer periods, enduring dust, vacuum, radiation, and prolonged changes in temperature. It must be a room surrounded by an environment in which a human being could not breathe for even a few seconds. On Earth, a home keeps the rain outside. On the Moon, the first human home must keep an entire atmosphere inside. Every joint, doorway, and pipe lies between two completely different worlds. On one side is a room with air, light, and temperatures suitable for human life. On the other is a vacuum, where even a single, unprotected breath cannot exist. This means a lunar habitat cannot simply be a room placed on the ground with its door closed. The entire structure must hold pressure inside while almost no air outside provides an opposing force. The walls are constantly pushed outward from within, much like the skin of a balloon trying to contain compressed gas. Every seam, seal, and opening through the habitat wall must withstand that difference for as long as people live there. A very small gap in a house on Earth may do little more than allow a draft or let rainwater seep inside. On the Moon, the same gap can become an escape route for air, gradually lowering the pressure within the habitat. Sensors must therefore monitor even the smallest changes continuously. If air begins to leak away, the crew must locate the breach, isolate the affected area, and repair it before the problem grows beyond their control. The entrance cannot open directly like the door of an ordinary home. If an astronaut pulled it open while the habitat was still filled with air, the atmosphere inside would immediately rush toward the vacuum outside. Instead, people must pass through an airlock, a small chamber positioned between the living area and the lunar surface. The inner door is sealed before air is removed from the chamber, and only then can the outer door be opened. When an astronaut returns, the process happens in reverse. They enter the airlock from the surface, close the outer door, and wait while the small chamber is filled with air again. Only when its pressure is nearly equal to that of the living area can the inner door be opened. This process keeps most of the base's atmosphere where it belongs, but every trip outside can still release some air and consume valuable time. A long-term base must therefore calculate how often the crew can go outside, how much replacement gas will be needed, and how the air inside the lock can be recovered before the outer door opens. More efficient systems may pump most of that air back into the habitat instead of allowing it to escape into the vacuum. But pumps, valves, and pipes are also components that can wear down. The more often the doors are used, the more frequently the entire mechanism must be inspected and maintained. The problem does not end when the outer door closes. A spacesuit returning from the surface carries something far more difficult to manage than it first appears. Lunar dust clings to boots, gloves, joints, cables, and nearly every surface that has touched the ground outside. When an astronaut enters the airlock, tiny particles can fall away, become suspended in the air, and spread into the living area, equipment, and filtration systems. This dust is not soft and loose like soil in a garden on Earth. It formed as fragments of rock were repeatedly crushed by impacts over billions of years. The moon has no rain, rivers, or wind to smooth the sharp edges of the particles. As a result, many of them resemble tiny shards of broken stone more than grains of weathered sand. Those sharp edges allow the dust to abrade surfaces whenever it is rubbed against them. It scratches glass, clings to fabric, and works its way into moving joints. A single tiny particle may not cause immediate damage, but thousands of repeated contacts over many weeks can wear through protective layers, make mechanisms harder to open and close, or gradually reduce the clarity of viewing windows. A long-term base cannot treat dust as nothing more than a housekeeping problem. Apollo astronauts encountered dust during every moonwalk. It coated their boots and the lower portions of their suits, then followed them back into the lunar module. The dust contaminated equipment, produced an unpleasant smell inside the cabin, and caused irritation in the noses and throats of some astronauts. Those missions lasted only a relatively short time, but the Apollo experience showed that dust would become one of the greatest challenges if humans remained on the moon for longer periods. A lunar home must therefore be designed from the beginning to prevent dust from entering. The area near the entrance should be separated from the main living space, so particles clinging to spacesuits cannot easily spread into the places where the crew sleeps, eats, and works. Surfaces should have few narrow gaps, be easy to clean, and avoid trapping dust in corners that are difficult to reach. The air filtration system must also be capable of capturing fine particles before they continue circulating through the habitat. One approach being studied is to keep the spacesuits outside or inside a separate compartment. An astronaut could enter through the back of the suit from within the base, seal it closed, and then detach the suit onto the surface. Upon returning, the astronaut would reconnect the suit to the hatch and step directly inside without bringing its dust-covered outer shell into the living area. This approach could reduce the amount of dust carried indoors, but it would still require airtight mechanisms capable of surviving repeated use. Doors, bearings, and joints must also be better protected. A dust particle trapped against a pressure seal can prevent the surfaces from pressing together as intended. Dust collecting on a hinge can increase friction and force the mechanism to work harder. A habitat therefore needs more than a strong outer shell. It also requires countless small components designed to keep functioning after repeated exposure to a dusty environment. In addition to mechanical methods such as brushing, vacuuming, or wiping, NASA has been testing technology that uses electric fields to remove dust. Thin electrode patterns placed across a surface can generate forces that move particles away from windows, solar panels, or radiators. This technology is often called an electrodynamic dust shield. Because it does not require a brush to scrape directly across the surface, it may reduce wear during cleaning. However, a technology that works in a laboratory or during a short mission has not necessarily solved the entire problem. Its effectiveness depends on particle size, surface shape, the amount of accumulated dust, and how long the system must operate. The electrodes also require electrical power, control circuits, and the ability to continue functioning through many thermal cycles. An electrodynamic shield is a promising tool, but a base will still need several layers of protection rather than relying on a single solution. Dust on a window may restrict visibility, but dust covering solar panels and radiators can directly threaten the base's survival. A thin layer on a solar panel can reduce the amount of light converted into electricity. Dust on a heat-radiating surface can make it more difficult for equipment to release excess heat. In an environment without air, thermal control depends heavily on surfaces specifically designed to absorb or radiate energy. On Earth, air moves around a building and helps carry heat away. People can open a window, turn on a fan, or use a cooling fluid to transfer heat into the surrounding environment. On the Moon, no outside air flows across the habitat walls. The structure receives heat from sunlight, electrical equipment, and the human body, but it cannot depend on wind for cooling. Heat must be conducted toward radiators and released into space as radiation. This creates a kind of paradox. The outer surfaces of the base must absorb enough energy to avoid becoming too cold, while also preventing excessive heating when exposed to sunlight. An area facing the sun may grow hot, while another section in shadow becomes extremely cold. The system must move heat from places where it is excessive to places where it is needed, while protecting pipes and machinery from prolonged temperature changes. The habitat may use multiple layers of insulation, reflective surfaces, and circulating fluid loops to keep the interior temperature stable. Pumps move fluid through warmer areas, carry heat toward radiators, and then return it to the system. Sensitive equipment may also require separate heaters during colder periods. If dust covers the radiators or solar panels, the challenges of thermal control and power generation can become more difficult at the same time. Another danger cannot be seen with the naked eye: radiation. Earth is protected by a thick atmosphere and a global magnetic field that reduce the impact of many high-energy particles from the sun and deep space. The Moon has no comparable layers of protection. An astronaut standing on the surface, or living inside a thin-walled habitat, would be exposed to a much stronger radiation environment than most people on Earth. On short missions, exposure can be managed through limited duration, careful scheduling, and close monitoring of solar activity. But when humans remain for weeks or months, the habitat must provide more substantial shielding. Materials brought from Earth can be arranged around living areas, while water and stored supplies may also absorb some of the radiation. A small storm shelter could be placed deeper within the structure for use during periods of intense solar activity. Lunar soil offers another possibility because it is already available on the surface. Instead of transporting all shielding material from Earth, robots could excavate the soil and pile it around the habitat. A sufficiently thick layer could reduce radiation while also helping protect the base from tiny meteoroid particles. This image is very different from the shining domes often seen in illustrations, but it is much closer to the practical needs of a shelter. We can imagine a robot moving slowly around a living module after it has been placed on the surface. The machine scoops up layer after layer of gray soil, pushes it against the walls, and gradually covers part of the roof. The work unfolds without any sound traveling through the vacuum, leaving only wheel tracks and new mounds of earth behind. After many hours or days, the habitat is no longer completely exposed, but begins to blend into the surrounding landscape. However, it cannot yet be said with certainty that the first habitat will be buried beneath the soil. Excavating and moving large amounts of material would require powerful robots, reliable electricity, and equipment capable of enduring dust for long periods. The ground would also need to be surveyed to ensure that inappropriate loads were not placed on the structure. Early missions may instead use shielding brought from Earth, bags filled with lunar soil, or localized protective walls until large-scale construction systems have been proven. Tiny meteoroids must also be considered in the design. Most are extremely small, and do not create the large, visible impacts we usually imagine. But because the moon has no atmosphere to burn them up, some particles can strike the surface directly at high speed. The chance of one hitting a habitat during a short mission may be relatively low, but a base operating for many years must account for the accumulated risk. The habitat shell may consist of several layers separated by empty spaces, allowing a small particle to break apart or scatter before it reaches the pressure-retaining wall. Lunar soil placed over the exterior could provide additional protection. The important point is that the habitat cannot be designed only for an ordinary day. It must continue protecting life even during rare events with potentially serious consequences. Every layer of protection adds mass, size, and complexity. A thicker habitat requires a larger rocket to carry it to the moon. Shielding transported from Earth takes up space that could otherwise hold food, scientific instruments, or spare parts. A construction robot needs its own power supply and transportation system. Designing a lunar base is therefore a constant balance between the level of protection required, the limits of launch vehicles, and the materials that can be obtained locally. The first habitat may not resemble a home in the familiar sense. It could be a cylindrical module, an inflatable structure protected by an outer shell, or several smaller compartments connected together. The interior may be narrow, with low ceilings and much of the available surface covered by wiring, pipes, and equipment. Every square meter may serve several purposes, from sleeping and working to storing supplies and providing shelter during emergencies. Large windows might create a stronger connection to the landscape outside, but they would also make the structure more difficult to protect. A window must withstand pressure differences, radiation, temperature changes, and the risk of impact. A realistic habitat may therefore have only small windows that are shielded when not in use, while most views of the outside come from external cameras. Living on the moon may be experienced through screens more often than through a broad wall of glass. Inside, sound would never disappear completely. Fans must push air through filters, pumps must move fluid through pipes, and electrical equipment must continue running. A home in the middle of a silent world could be filled with the constant hum of machinery. When a familiar sound suddenly stops, the crew may immediately recognize that a system needs attention. What makes the habitat a home is not its external shape, but its ability to recreate ordinary experiences within an extraordinary environment. Astronauts can remove their helmets, breathe, drink water, and sleep without carrying life support systems on their backs. They can set down their tools, repair a component, and speak to one another without being separated by glass and vacuum. But for those moments to exist, the entire structure must continuously keep the outside world where it belongs. The vacuum must stop at the habitat walls. Dust must stop near the entrance. Radiation must be reduced by the surrounding materials. Heat must be released at the proper rate, while the air inside continues to circulate. The image of a lunar base should therefore not begin with transparent domes, rows of green trees, or brightly lit roads. It begins with a tightly closed door, a seal that does not leak, and a filter that continues keeping dust out of human lungs. These details are less spectacular than a rocket launch, but they determine whether the crew will wake up the following day. Outside, robots may still be pushing soil against the living module. Protective shutters are closed over the windows, while dust is removed from spacesuits in a separate area. An astronaut enters the airlock, seals the door leading to the surface, and waits as the system begins pumping air into the chamber. The pressure rises gradually, the sound of the fans returns, and the indicators change from warning states to safe conditions. Then the inner door opens. The dust remains behind, while ahead lies a small room filled with air, light, and temperatures suitable for human life. In a world with no atmosphere at all, that room is like a fragile pocket of air held together by metal, fabric, pipes, and careful engineering. A sealed room can protect people for a few hours, but to live for weeks, that room must continuously perform a task that Earth provides for free, creating breathable air and preserving every drop of water. Every time an astronaut exhales, the room receives more carbon dioxide. Every time they wash their hands, clean water becomes wastewater. Every drop of sweat, every breath, and every trace of moisture touches the walls of the habitat before entering an invisible cycle. On Earth, these things can easily disappear into a vast world. On the Moon, almost nothing can be allowed to disappear. Morning at the base does not begin with birdsong or sunlight passing through a window. It begins with the steady hum of fans inside the ventilation ducts, the sound of pumps moving water through the system, and artificial lighting that changes to signal the start of a new day. The astronauts open their eyes inside a sealed room, where every breath depends on machines that have been running continuously through the night. The air inside the habitat cannot simply be pumped in once and left unchanged forever. The human body continuously consumes oxygen and releases carbon dioxide, water vapor, and heat. Without a treatment system, the composition of the air would change hour by hour. Oxygen levels would gradually fall, carbon dioxide would rise, and moisture would collect on cold surfaces until the room was no longer suitable for life. On Earth, plants, oceans, and the atmosphere participate in vast cycles that help maintain a habitable environment. A lunar base has no entire planet supporting it from behind. It must compress some of those functions into a small network of pipes, filters, and pumps. Each device performs a very specific task, but together they must produce something that seems remarkably simple, a room where humans can continue to breathe. Sensors continuously measure oxygen, carbon dioxide, humidity, temperature, and any gases that may be released by equipment or materials inside the habitat. Most of the time, the crew does not see this process taking place. They know the system is working because the readings remain within safe limits, and the fans continue to hum steadily. When a value begins to change, an alarm may appear before the human body has time to notice that anything is wrong. Carbon dioxide is one of the substances that must be removed most frequently. Each person exhales only a small amount with every breath, but inside a sealed space, those small amounts quickly accumulate. The ventilation system must carry air from every part of the habitat to the processing unit, because carbon dioxide cannot be allowed to collect around sleeping or working areas. Once cleaned, the air returns to the cabin and begins another cycle. Oxygen must also be replenished. Some of it can be brought from Earth in storage tanks, especially during the earliest missions, when surface stays are still brief. But if humans remain for weeks or months, relying only on stored gas would greatly increase the amount of cargo that must be transported. A long-term system must find ways to produce additional oxygen from available resources, and water is one of the most important possibilities. Water can be separated into oxygen and hydrogen using electricity. The oxygen is released into the habitat for the crew to breathe, while the hydrogen may be handled in different ways depending on the system's design. This process is not a form of magic that creates matter from nothing. It consumes both water and electricity, so it is useful only if the base has a stable water supply and a power system capable of operating continuously. The air also contains more than oxygen and carbon dioxide. Odors from food, the human body, new materials, cleaning products, and electrical equipment can all accumulate inside a sealed environment. Substances that would barely be noticed on Earth can quickly become unpleasant when there is no window to open and no outside breeze to carry them away. The filters must therefore capture not only dust, but also many other impurities in the air. Humidity must be controlled as well. The human body continuously releases water vapor through breathing and the skin, especially during exercise or demanding physical work. If humidity becomes too high, water may condense on pipes and cold surfaces, creating a risk of corrosion or damaging electrical equipment. If the air becomes too dry, the crew may experience discomfort in their eyes, skin, and respiratory systems. Condensed water is not treated as useless excess. It is collected, sent through the treatment system, and returned to the base's usable water supply. Moisture from breathing, sweat after exercise, and water evaporated during daily activities can all re-enter the cycle. A single drop may be used many times, passing through several different forms before appearing once again in an astronaut's cup. The International Space Station has become an important laboratory for this process. For many years, crews aboard the station have lived in an environment where air and water must be managed with great care. Its systems recover moisture from the cabin and process several kinds of wastewater for reuse. The experience accumulated in orbit has helped engineers understand which filters clog easily, which pumps need replacement, and which components begin to deteriorate after long periods of operation. An astronaut on the moon may wake up, use a small amount of water to wash their face, and then drink the water prepared for the morning. That water did not come from a river, a reservoir, or a pipeline connected to a nearby city. It may once have been moisture in the air, water used the previous day, or liquid recovered through the treatment system. What matters is not where it came from before, but that it has been purified enough to be used safely again. After breakfast, the crew begins exercising. Their bodies produce heat and sweat, increasing the humidity inside the habitat. Fans draw the moist air through a condensing unit, where the water vapor is returned to liquid form. That water is not discarded. It is sent into the treatment system along with other sources, because every drop that is lost means a future supply mission must carry more mass from Earth. Recycling water does not mean that every drop can be preserved forever. Some may escape when an airlock is opened, remain trapped in materials, or prove impossible to recover completely from waste. The system also needs water for tasks that do not feed directly back into the drinking supply, such as cleaning equipment or processing certain materials. Even a base with highly effective recycling will therefore need additional sources. Filters do not last forever. Over time, they capture enough contaminants that their performance begins to decline, requiring them to be cleaned or replaced. Pumps can wear down, valves may fail to seal completely, and sensors may begin reporting inaccurate measurements. A recycling system that works well for several weeks may not continue operating perfectly for many months without maintenance. This makes spare parts part of the life support system itself. A backup pump, a fresh filter, or a replacement section of pipe may not appear as impressive as a rocket or lunar lander, but any one of them could determine whether the base continues operating or the mission must end early. Every component must be selected according to its mass, durability, and the crew's ability to replace it inside a confined space. The base also cannot allow a single device to become a point of failure for the entire crew. If there is only one carbon dioxide removal unit and it stops working, the air could become dangerous long before a rescue spacecraft could arrive. Critical functions, therefore, usually require backup systems, or at least a temporary alternative. The crew must know how to switch to a second unit and isolate the damaged section without interrupting the operation of the entire base. However, backup systems also increase the amount of mass that must be delivered to the moon. Every second machine takes up additional space, requires more wiring, and may need its own replacement parts. Designing a base is therefore always a balance between safety and transportation limits. Too little redundancy leaves the crew vulnerable, while too much equipment can make the mission heavier, more complicated, and more difficult to build. The risk of fire must also be monitored carefully. Inside a sealed room containing oxygen, smoke cannot escape through a window, and firefighters cannot arrive from outside. Sensors must detect unusual heat, smoke, or substances released when materials begin to overheat. The crew needs fire suppression equipment, protective masks, and procedures for isolating an area before flames can damage the air support systems. Even after an incident, smoke and toxic compounds may remain inside the habitat. Filters must clean the air while the crew checks whether wiring, materials, and equipment are still safe. A room may appear normal again, while still containing substances that cannot be seen. Sensors therefore become additional senses for humans in an environment where many dangers have no obvious color or sound. Life inside the base is always accompanied by the background noise of machinery. The sound of a fan is more than simple noise. It means air is still being carried to the filters and returned to the living area. The sound of a pump indicates that water is still moving through the system. The crew may become so accustomed to these sounds that they notice them only when one changes or suddenly disappears. At night, when most scientific equipment is temporarily shut down and the lights inside the habitat are dimmed, the life support system continues working. Humans still breathe while they sleep, still producing carbon dioxide and moisture. Water must still be recovered, heat must still be controlled, and air must continue circulating through every section. A lunar base never completely rests, because the life inside it never stops interacting with its environment. Smell is another rarely discussed part of long-term life in space. Heated food, worn clothing, sweat after exercise, and everyday supplies all release different compounds. On Earth, people can open a door or step outside to find fresh air. On the Moon, every odor must either be removed by the filtration system or remain within the same small space. Bathing with large amounts of water will be almost impractical in the earliest bases. The crew may use damp towels, limited quantities of water, and hygiene methods that produce less waste. Clothing will also be difficult to wash in the usual way, because every laundry cycle requires water, electricity, and dedicated equipment. Even the smallest details of daily life must change in a place where every resource is finite. Waste cannot simply be carried outside and abandoned. A bag of trash left on the surface could contaminate a working area, become a moving hazard when a spacecraft launches, or occupy space needed for equipment. Inside the base, waste must be sorted, compressed, and stored. Some materials may be processed to recover water or be used again, but many items will still have to wait for a future transport mission or be managed safely in another way. Every bag of waste therefore becomes a logistical problem. It has mass and volume, and it may contain odors or microorganisms. The base must keep waste away from water supplies and living areas, but interior space is extremely limited. As a mission continues, the amount of trash grows each day, making methods for reducing its volume and reusing materials increasingly important. During the first missions, most food will still need to be transported from Earth. It must be lightweight, remain edible for long periods, and require little water or energy to prepare. Astronauts may heat individual meals, add water to dried foods, or eat items that have already been packaged. Meals provide more than energy. They also create a shared moment in a room otherwise filled with constant work. Living on packaged food for many weeks may satisfy basic nutritional needs, but it offers little sense of freshness. A few small plants could add leafy greens, flavor, and variety to meals. They could also provide psychological value, because the green of living leaves would be one of the few signs of natural life among the metal, plastic, and gray soil outside. Still, a few trays of plants would not turn the first base into a self-sufficient farm. Plants require water, light, nutrients, and space. They also produce humidity and biological waste and require regular care. Growing enough food to support an entire crew would demand a system far larger than the small plant experiments likely to be conducted during the early stages. At first, plants may serve as a supplement rather than the main source of food. A few fresh leaves could improve a meal, but most calories would still come from supplies transported from Earth. This means every resupply mission would need to carry food, filters, medicine, replacement parts, and many other consumable materials. The base could not yet survive in complete independence simply because it was able to recycle water and air. The idea of a closed-loop system must therefore be understood carefully. A system may reuse most of its water, produce some oxygen, and process many kinds of waste, yet still require energy, replacement parts, and additional raw materials. No machine can operate forever on its own. Every cycle loses a small amount, and those losses gradually become significant as time passes. Living on the Moon for long periods requires systems that perform well, not only under normal conditions, but also when the crew exercises more heavily, when a piece of equipment generates additional heat, or when dust enters the habitat after a moonwalk. The number of people inside the base directly affects oxygen consumption, water use, and waste processing capacity. A system designed for 4 people may not be able to support 6, even if there is still enough physical space for them. Each additional crew member increases the amount of air that must be processed, water that must be recycled, and food that must be stored. But a larger crew also provides more people to perform repairs and share the workload. The base must balance crew size against the capacity of its entire support system. Engineers cannot simply enlarge the living area and assume that the existing pipes and filters will automatically meet the new demand. The earliest missions will provide real data about how much water each person uses, how often filters need replacement, and which devices require the most frequent maintenance. Calculations made on Earth are only a starting point. Once people actually live inside a lunar base, their daily habits, the dusty environment, and the pace of their work may create demands that were not fully anticipated. A pump may wear out faster because dust reaches a technical compartment. Opening the airlock may release more air than expected. A material may begin producing an odor after prolonged exposure to radiation and temperature changes. These small problems will shape the design of future bases, just as experience aboard the International Space Station has influenced many of the systems now being prepared for deep space. At the end of the day, the crew gathers its tools, checks the remaining water supply, and reviews the air quality readings. The filters continue working while newly collected waste is compressed and moved into storage. The lights inside the habitat gradually dim to help the body maintain a sleep cycle similar to a day on Earth. Outside, the sky remains black, and the landscape does not change in familiar ways. A person may lie down, close their eyes, and briefly forget that there is no air beyond the habitat wall. But the room cannot afford to forget. It must continue holding pressure, regulating humidity, and removing carbon dioxide from every breath. A small fan keeps turning in the darkness, performing work that on Earth is shared by winds, plants, oceans, and an entire vast atmosphere. Life on the moon therefore depends not only on enormous rockets or landers standing dozens of meters tall, it also depends on a valve closing at the right moment, a sensor providing accurate information, and a filter continuing to capture contaminants after weeks of use. These small devices rarely appear in spectacular images, but they determine whether the crew will still be able to breathe when they wake the following morning. An effective recycling system can extend the life of water brought from Earth. It can recover moisture, process used water, and return some of it to a drinking cup. But even the most efficient system cannot preserve a finite supply forever. Some water will still be lost, some will remain trapped in waste, and demand will continue to grow as surface stays become longer. To remain for longer periods, humans cannot merely protect every drop of water they bring with them. They must find more water in the very place that appears driest of all, within regions that never receive sunlight and are cold enough to preserve material for billions of years. At the bottom of certain craters near the moon's south pole, the sun never rises above the rocky rim. Temperatures there are so low that a water molecule entering the region may remain trapped for an extraordinarily long time. There are no rivers, no lakes, and no broad sheets of white ice like those found in Earth's polar regions. There may only be grains of ice mixed into dark soil, resting in places where no human being has ever walked. These areas are known as permanently shadowed regions. Because the moon's rotational axis is tilted only slightly, the sun at both poles always moves close to the horizon. Sunlight may reach elevated ridges, but it never touches the floors of some deep craters. Within that enduring darkness, temperatures can fall below -240 degrees Celsius, turning the depressions into cold traps capable of preserving water and other volatile substances for billions of years. But the search for lunar water did not begin with humans descending into those craters. The first clues were detected from orbit by instruments that did not directly observe a block of ice, but instead measured unusual properties of the surface. In the 1990s, the Clementine spacecraft suggested that shadowed regions near the poles might contain ice, while Lunar Prospector later detected elevated concentrations of hydrogen in areas that receive no sunlight. Hydrogen does not automatically mean water, but it made the idea of a completely dry moon increasingly difficult to accept. In 2009, the LCROSS mission took the search a step further. A rocket stage was deliberately sent crashing into Cabeus crater near the South Pole, throwing up a plume of material that may have remained in darkness for billions of years. LC-CROSS flew through the debris and analyzed its composition before also striking the surface. The measurements confirmed that water was present in the released material, including relatively pure grains of ice in some areas. Data from the Moon Mineralogy Mapper aboard Chandrayaan-1 later provided clearer spectral evidence of water ice at the surface of certain shadowed regions near both poles. The instrument did more than observe the brightness of the material. It also detected the distinctive way ice absorbs specific infrared wavelengths. This allowed scientists to distinguish solid ice from signals that revealed only hydrogen or minerals containing hydroxyl groups. For many years, these discoveries created an image in which ice was concentrated mainly inside a few large, deep, and exceptionally cold craters. However, An analysis of lunar reconnaissance orbiter data, published in 2024, suggested that signs of ice may be distributed more widely across permanently shadowed regions, extending away from the South Pole to roughly 77 degrees south latitude. The coldest locations, particularly near the bases of slopes facing toward the pole, are expected to contain higher concentrations of ice than the warmer areas around them. This may sound like an enormous reservoir of water waiting to be used, but orbital data cannot yet reveal exactly how much ice is present at each location. Scientists still do not know whether the richest deposits form continuous layers, whether they lie directly at the surface, or whether they are buried beneath dry soil. Current maps indicate where ice is more likely to be found, but they cannot yet direct an excavator to the exact place where digging should begin. Lunar ice may not resemble the block of ice inside a freezer. It could exist as tiny grains scattered among soil and rock, thin coatings attached to the surface, or concentrated deposits at different depths. A cubic meter of soil may contain enough ice to be scientifically significant while still holding too little to extract efficiently. Elsewhere, the concentration may be greater, but the deposit could lie on a slope that is too dangerous to reach, or inside a region so cold that equipment struggles to survive. This is the distance between knowing that a resource exists and knowing whether it can actually be used. A hydrogen signal observed from orbit may stretch across many kilometers, but a base cannot drink a signal. Before water can appear in an astronaut's cup, humans must locate it, measure its concentration, understand its depth, and bring machinery to the site. Each step introduces another problem that maps viewed from above cannot completely solve. Viper was designed to narrow that gap. The rover carries several scientific instruments and a drill capable of reaching approximately 1 meter beneath the surface, allowing it to examine soil at different depths and under different temperature conditions. After the original plan was discontinued because of rising costs and delays, NASA selected Blue Origin to deliver Viper to the South Polar region aboard the Blue Moon Mark 1 lander, with the goal of placing the rover on the surface in late 2027 if preparations proceed as planned. Viper was not created to excavate a large-scale water mine. Its mission is expected to last around 100 days and focus on 3 more practical questions: where the ice is located, how much of it exists, and how accessible it may be to humans. The rover can travel through areas with different temperatures, measure signs of hydrogen, and then drill into the soil at selected locations. Results from each site will help connect signals detected from orbit with what truly exists beneath its wheels. In the South Polar region, simply delivering a rover to the area it needs to investigate is already a challenge. Low-angle sunlight creates long shadows and makes the terrain difficult to evaluate. Permanently shadowed regions may contain more ice, but they are also the coldest places and receive no sunlight for directly recharging solar batteries. Viper must plan routes between its scientific targets and locations, with conditions more suitable for maintaining electrical power and safe operating temperatures. As the rover approaches a cold region, its sensors may begin searching for signs of hydrogen beneath the surface. A stronger signal suggests that the area deserves closer examination, but it still does not reveal the form in which the water exists. The drill must penetrate the soil and bring material up from different depths for analysis. The upper layer may be nearly dry, while soil several dozen centimeters below contains more ice, or the ice may occur only in small, discontinuous patches. Each drill hole represents only a very small point across an enormous landscape. One detection of ice does not automatically mean that the entire surrounding region is the same. The rover must repeat its measurements at many locations across different terrain types and temperatures. Only from these individual points can scientists begin constructing a 3-dimensional map of how water is distributed through the soil near the surface. Even if that map reveals an ice-rich region, extraction would still require an entire chain of equipment that does not yet fully exist on the Moon. First, robots or astronauts would have to bring machinery to the site. The route might cross slopes, poorly illuminated regions, and loose soil that causes wheels to slip. If equipment cannot reach the deposit regularly or carry material back to the base, even a large amount of ice would be difficult to turn into a practical resource. The soil would then have to be excavated or drilled. On the Moon, sharp dust can enter bearings, wear down surfaces, and cling to components that need to move. In the extreme cold of the polar regions, lubricants, batteries, and other materials may behave differently than they do inside laboratories on Earth. An excavator must not only be powerful enough to collect soil, but also capable of operating through many cycles without a repair crew standing nearby. The extracted material would not yet be drinking water. If the ice is mixed with soil, the mixture must be placed inside a sealed chamber and heated. As the temperature rises, the ice turns into water vapor and separates from the dry soil. That vapor must be captured before it escapes into the vacuum, then cooled or compressed until it returns to liquid form. Every pipe, seal, and condensing surface must keep the water contained within an environment that is constantly trying to draw it away. The water collected may still not be clean enough to enter the habitat's life support system directly. Permanently shadowed regions may preserve carbon dioxide, ammonia, methane, sulfur, and many other volatile substances alongside the water. For science, this mixture is extremely valuable because it may record the history of material that once reached the moon. For the crew, however, it means the water must be analyzed and purified before it can be used for drinking, hygiene, or oxygen production. Once purified, the water needs to be stored somewhere that prevents it from freezing unintentionally or escaping. Storage tanks must withstand pressure, temperature changes, and vibrations caused by activity around the base. If the water must be transported from the extraction site to the habitat, pipes or transport vehicles will have to cross uneven terrain. A water source only a few kilometers from the base may appear close on a map, yet still require an entire logistical system to use regularly. Energy is involved in almost every step. Excavators need electricity, processing chambers require heat, pumps must move vapor and liquid through pipes, and filters must continue operating. If humans want to separate water into oxygen and hydrogen, even more electricity will be needed. A region rich in ice but far from a reliable power source may therefore be less useful than a region containing less ice that is easier to reach and operate within. This is why lunar ice cannot be treated as fuel already waiting underground. Water can be electrolyzed into hydrogen and oxygen, two components that can be used in certain types of rocket propellant. But once produced, those gases must still be cooled, compressed, or converted into a form suitable for storage. Hydrogen is especially difficult to contain because its small molecules can escape through many materials, while keeping it at extremely low temperatures requires additional energy. If the entire chain can be made to work, lunar water could serve several purposes. Its first and most direct role would be to provide drinking water and support hygiene for the crew. Some could be used to produce oxygen for the habitat's atmosphere. Water could also be positioned around living areas to help reduce radiation exposure, because hydrogen atoms can absorb some of the energy carried by passing particles. The possibility of producing propellant is why water ice is often described as the foundation of a refueling station beyond Earth. The idea is compelling because fuel that does not have to be lifted entirely from Earth's surface could reduce launch mass for certain missions. But between a soil sample containing ice and a continuously operating fuel depot lie a mine, a processing plant, a power source, storage tanks, transportation systems, and many years of testing. Calling the moon a ready-made gas station would therefore go beyond what current evidence supports. We know that ice exists in the polar regions, but we do not yet know how much can be extracted at a reasonable cost. Nor do we know whether the richest deposits lie in places that machinery can reach easily. A resource becomes truly useful only when the energy and equipment required to obtain it do not exceed the value it provides. A region may be extremely important to science while remaining unsuitable for extraction. Its ice may preserve information about comets, meteorites, the solar wind, and the history of water moving across the lunar surface. Large-scale excavation could destroy a natural record that has survived for billions of years. Humans will therefore have to decide which areas may be used as resources and which should be preserved for scientific study. Those decisions must be made before activity expands. If several nations and companies begin searching for water near the South Pole, their routes, landing zones, and extraction sites may lie close together. Exhaust from one landing spacecraft could blow dust onto another group's equipment. Excavation could also alter the delicate environment of a permanently shadowed region. Water is not only an engineering challenge, but also a question of how to manage a limited resource. During the early years, the greatest value of lunar ice may not be the amount of water produced. It may lie in the data that reveals what is actually beneath the soil. A rover discovering an ice-rich layer 40 centimeters below the surface could change the way excavators are designed. A region thought to contain abundant water but found to be nearly dry could prevent a base from being placed in the wrong location. Viper is not the only robot involved in the search. NASA is also providing a water detection instrument for the LUPEX rover led by Japan and India, which is targeting a polar mission no earlier than 2028. Other instruments may measure hydrogen from the surface or from orbit. Each mission observes the moon in a different way, and only by combining their data will the lunar water map gradually become more reliable. The results may show that the ice is concentrated in small pockets, making extraction more difficult than expected, or they may reveal water-rich layers beneath the surface in regions that robots can reach relatively easily. Until a drill actually enters the ground and samples are analyzed on site, both possibilities remain open. Hope should remain, but it should never replace measurement. Imagine a future machine stopping at the edge of a shadowed region. It drills into the frozen soil, carries the material into a sealed chamber, and begins to heat it. After a time, a thin layer of vapor appears along the wall of a pipe, travels toward a condenser, and gathers into a single, small drop of water. That drop has never flowed through a river, never fallen as rain, and may have remained motionless in darkness since long before humans existed. This has not happened yet, nor would it prove that a lunar base had become self-sufficient in water. But if the first drop is someday extracted from lunar soil, it will mark an important change. For the first time, humans will not merely carry life from Earth to another world, but begin using the material of that world itself to sustain life. Water ice is not a miracle that solves every problem. It will not flow to the base on its own, transform itself into oxygen, or fill propellant tanks without assistance. But if humans can locate deposits with enough ice, build machinery that survives the cold, and provide sufficient energy, that water could gradually reduce absolute dependence on every shipment from Earth. Ice becomes water only when heat is available. Water becomes oxygen and propellant only when electricity is available. And on the moon, that power must continue operating through shadowed regions, keep machinery from freezing, and protect the base through a night that can last nearly half an Earth month. When the last sunlight leaves a solar panel, the base does not immediately fall silent. Stored batteries begin supplying electricity. Heaters keep equipment from freezing. Fans continue pushing air through filters, and pumps still move water through the pipes. Inside the habitat, everything may appear unchanged, but with every passing hour, the remaining energy supply grows a little smaller. On Earth, darkness usually lasts only through the night. By morning, sunlight returns, solar panels begin producing electricity, and many systems can be recharged. Across most of the moon's surface, that cycle unfolds far more slowly. From one sunrise to the next takes about 29.5 Earth days, which means a period of daylight or darkness in many regions can last nearly 2 weeks. A lunar base therefore cannot prepare for only 8 or 10 hours without sunlight. It must sustain life for hundreds of hours while the solar panels produce no energy and the temperature outside continues to fall. The air must still be filtered. Water must keep circulating. Communication equipment must remain active, and the habitat must stay warm enough for both humans and machinery. Near the South Pole, the situation is more complicated than an ordinary cycle of day and night. The sun always remains very low, appearing to slide around the horizon rather than climbing high into the sky. A ridge may receive light for much of the time, while the valley beside it remains in prolonged shadow. At the bottom of certain deep craters, direct sunlight has not appeared for billions of years. These differences make the choice of a base location especially important. An elevated area receiving more sunlight may be favorable for solar panels, but it may not be flat or close to deposits of water ice. A lower region may lie near valuable scientific targets, yet endure long periods of darkness and extreme temperatures. A difference of only a few hundred meters in terrain can sometimes create two completely different energy environments. Solar power remains one of the most useful options for the early stages. Panels can be deployed relatively quickly, require no continuing supply of fuel during operation, and generate electricity whenever sunlight reaches them. If placed on elevated slopes or locations with favorable illumination, they could provide power for habitats, scientific instruments, communication systems, and vehicles working near the base. But solar panels on the moon cannot simply be laid flat and left in place. Because the sun remains low, their angle must be carefully calculated to capture light efficiently. The shadow of a hill, or even a large piece of equipment, could cover a significant portion of the array. Lunar dust may also settle on the panels, reducing the amount of light reaching the photovoltaic cells and requiring robots or dust removal systems to clean them. Electricity could be carried from well-lit regions to the habitat through cables. Robots might pull these cables across the surface, connect small power stations, and gradually form a larger network. In the future, some equipment may also be charged wirelessly at fixed locations. NASA is currently studying robot-deployed cables, dust-resistant connectors, and methods for recharging rovers as part of a gradually expanding lunar power infrastructure. A cable on the moon must do more than conduct electricity. It must withstand severe temperature changes, sharp dust, and the possibility of damage from wheels or other equipment. Its connectors must continue working after repeated assembly, even when dust has settled on the contact surfaces. If the cable crosses uneven terrain, it must also avoid places where it could be stretched, buried, or disconnected from the rest of the power network. The base cannot depend on a single cable either. If a rover accidentally damages one line or a connector stops working, the entire habitat cannot be allowed to lose power. The network needs multiple branches, switches capable of isolating damaged sections, and backup sources strong enough to maintain essential functions. Like the circulatory system in a body, electricity needs another route when one path is temporarily blocked. While sunlight is available, some of the electricity must be used to charge batteries. These batteries store energy chemically and release it again when the solar panels stop producing power. This familiar method may be enough for short interruptions, but sustaining a base through hundreds of hours could require an enormous mass of batteries, especially when the habitat, extraction equipment, and several rovers are all consuming electricity. Batteries do not retain their original capacity forever. Each cycle of charging and discharging changes their internal materials slightly, causing performance to decline over time. Extremely low temperatures can reduce their efficiency or damage them if they are not heated. The equipment used to store energy must therefore consume some of that same energy simply to protect itself during prolonged darkness and cold. Fuel cells offer another possibility. These systems can combine hydrogen and oxygen to produce electricity, while also generating water and heat. During periods of abundant solar power, the base could use that energy to prepare the necessary materials and then consume them during darkness. However, the gases must be produced, purified, and stored safely. So, the complete cycle requires additional tanks, pipes, and control systems. No single solution will be suitable for every device. A living module needs a large and stable supply of electricity, while a small sensor may require only enough heat to avoid freezing. A moving rover has different needs from a stationary scientific station. The base may therefore have to combine several sources: sunlight whenever it is available, batteries for interruptions, small heat sources for individual instruments, and a more powerful system for long-term operations. Radioisotope heater units could help small devices survive periods of extreme cold. They use the natural heat produced as radioactive material decays, rather than a reactor that can be switched on and controlled as needed. Their primary purpose is to keep batteries, electronics, and mechanical components within suitable temperature ranges, not to provide large amounts of electricity for an entire habitat. NASA is working toward testing devices like these during the early stages of moon-based development. The next step is the radioisotope thermoelectric generator, commonly known as an RTG. This device converts part of the heat from radioactive decay into electricity, but its output is generally better suited to robots, scientific instruments, or limited systems. An RTG can operate without sunlight and support exploration in shadowed regions. But it is not designed to power an entire base by itself, including its habitats, machinery, and extraction operations. Fission power is intended for a different scale. Instead of relying only on heat from natural radioactive decay, the system produces energy through controlled fission reactions inside a small reactor. It could provide continuous electricity, whether the sun is shining or hidden behind the terrain. NASA and the United States Department of Energy are currently working together to develop a fission power system for the lunar surface, though its deployment date will still depend on design, testing, and safety preparations. One design under study falls within a power range of approximately 40 kilowatts, enough to operate several important systems for long periods without depending directly on lighting conditions. That figure does not mean one reactor could immediately meet every need of a large base. Mining, oxygen production, heating, and the charging of multiple rovers could quickly increase demand, requiring the electrical network to continue expanding. Fission power is also not guaranteed to be the first option deployed. The reactor must be delivered safely, installed at an appropriate distance from the living area, and connected to the electrical grid. The system requires heat rejection, shielding, and control mechanisms capable of operating for years. Every stage demands rigorous testing, because a reliable power source must continue functioning while the nearest repair team remains on Earth. Nuclear power should therefore not be seen as a solution that instantly makes the problem of the lunar night disappear. It is an important possibility that could complement solar energy and energy storage. A practical base may use several sources at the same time, ensuring that a failure in one system does not shut down the entire network. Resilience comes from coordination and redundancy, not simply from the strength of one machine. During periods of darkness, the base must decide which systems receive priority. Air, water, temperature control, and communication will always remain essential. Some experiments may be paused, rovers may enter energy-saving modes, and extraction activities may be reduced. Managing electricity during this time resembles managing the remaining water on a long journey. Every use must be weighed against the time left before the main supply returns. If stored energy falls faster than expected, the system may automatically shut down non-essential equipment. Lighting in some areas may be dimmed, storage compartments may be allowed to become cooler than the living quarters, and the crew's work schedule may be adjusted. Human life continues, but the base gradually contracts, preserving only its most essential functions until conditions improve. Electricity also determines how far humans can travel from the habitat. An astronaut on foot can carry only a limited supply of oxygen, battery power, and cooling capacity. Rovers extend that range by transporting people, equipment, and samples across a wider area. But every kilometer traveled away from the base requires enough energy for the rover to return, because there are no gas stations, power lines, or rescue teams waiting along the route. The first rovers may carry astronauts while also transporting cargo between landing zones, habitats, and scientific stations. They could pull cables, move materials, or deliver equipment to extraction sites. Later generations may include pressurized cabins, allowing people to travel for several days without wearing spacesuits continuously. NASA is currently working toward developing several types of surface vehicles for transportation, site preparation, excavation, and logistical support around the South Pole. Even when no crew is present on the moon, rovers could continue working. They might survey routes, inspect solar panels, move cargo, or observe equipment showing signs of trouble. Autonomous operation becomes important because, although a signal traveling between Earth and the Moon takes only a little more than 1 second in each direction, human operators still cannot respond instantly to every rock, small crater, or change in terrain. An autonomous rover must be able to see its route, evaluate slopes, and recognize obstacles beneath long shadows. At the South Pole, one side of a rock may be brightly illuminated while the other nearly disappears into darkness. New prototypes are being tested on steep terrain and under lighting conditions resembling dawn, dusk, or night to reproduce some of these challenges. However, their durability through repeated cycles of cold and lunar dust must still be demonstrated through actual operations. If a rover travels behind a ridge, it may lose direct visibility of the base or Earth. Radio signals travel along nearly straight paths and can be blocked by terrain. A vehicle with a full battery and fully functional systems may temporarily lose communication simply because a crater wall lies between it and the transmitter. Expanding the range of surface travel therefore requires a broader communication network as well. On Earth, phones and vehicles can rely on multiple GPS satellites to determine their positions almost continuously. The Moon does not yet have a complete equivalent system covering its surface. Rovers and astronauts must combine maps, inertial sensors, terrain imagery, signals from Earth, and relay stations. As activity expands, these separate methods will need to be connected into a more stable and dependable service. LunaNet is being developed as a shared framework through which systems belonging to different nations and organizations can provide communication, positioning, navigation, and timing services around the Moon. It is not a single satellite or a completed network, but a collection of standards intended to help different relay systems work together. The architecture is designed to support spacecraft in orbit, equipment on the surface, and vehicles moving between different regions. NASA is also developing the Lunar Communications Relay and Navigation Systems, in which orbiting satellites could relay signals between users on the surface and Earth. These satellites may also transmit data that helps rovers determine their position and velocity. Under the current Moon base plan, the initial relay network could gradually expand into multiple satellite groups and surface infrastructure, increasing both coverage and redundancy. Imagine a rover traveling beyond the base's direct line of sight. Behind it, a crater wall has hidden the communications antenna, while ahead lies a route toward an ice-bearing region. Instead of stopping completely, the rover sends a signal to a satellite passing overhead. The data is relayed back to the base. Its position is updated, and the vehicle continues its journey without needing to see the place it left behind. That communication network also requires electricity. Satellites must keep their equipment operating in orbit, surface stations must maintain their antennas, and rovers need enough energy to transmit signals. If power begins to fall, communication may weaken at the very moment a vehicle needs help most. Energy, mobility, and navigation are therefore not three separate problems. They are interdependent parts of the same system. Inside the base, a screen may display the locations of the rovers, their remaining power, and the condition of the network. The crew cannot see electricity flowing through the cables, but they experience it in every activity. The lights remain on, the air continues to circulate, and data from vehicles beyond the horizon continues to appear. Electricity becomes the heartbeat on which the entire base depends, yet rarely notices while it remains steady. Eventually, a long period of darkness begins to approach its final hours. The batteries have endured hundreds of small cycles of power delivery. Heaters have continuously protected essential equipment, and many non-critical activities have been suspended. Outside, rovers remain still at charging stations, while scientific outposts maintain only their most essential sensors. The base is still alive, but that life has been reduced to every remaining watt of power. Along the horizon, the first band of light begins to touch a ridge. It moves very slowly, at first revealing only the outline of the terrain against the darkness. Then the sunlight reaches a solar panel positioned on higher ground, spreads across its dust-covered surface, and begins producing electricity. Indicators inside the habitat change. The batteries shift from discharging to charging, and systems that had been resting gradually awaken. No cheering can travel across the surface, but the base has survived a long night. The fans are still running, water remains inside the pipes, and the rovers outside can begin operating again. Electricity has done more than keep the equipment alive. It has preserved a tiny fragment of Earth's environment on a world with no stable sunlight, no natural electrical grid, and no native life. Once the habitat has air, water, and electricity, its most important machines may appear to be ready. But the next challenge no longer lies only within pipes, cables, or solar panels. It lies within the human body itself. A body shaped by Earth's gravity that must now live for long periods under a gravitational pull only about 1/6 as strong. When they return, astronauts must inspect their bodies just as they inspect their equipment. They look for signs of muscle pain, joint strain, dehydration, or discomfort caused by heat. A small scratch on Earth may be simple to treat, but on the Moon it must be monitored to prevent infection or interference with the ability to wear a spacesuit. Every change is recorded because a doctor cannot physically enter the base to examine them. Communication time between Earth and the Moon is far shorter than it would be with Mars. A conversation can still take place almost normally, even though the signal takes more than a second to travel in each direction. Doctors on Earth can review data, guide an ultrasound examination, or help assess a condition. But they cannot personally place a stitch, stabilize a broken bone, or move a patient onto an operating table. The crew must therefore be capable of handling many situations on their own. At least some members need enough medical training to evaluate injuries, administer medication, and perform basic procedures. Medical equipment must be small and lightweight, yet versatile enough to support everything from routine examinations to emergencies. A compact ultrasound device could replace several larger machines if the person using it receives proper guidance from Earth. Medication raises its own questions. It must be stored at stable temperatures and protected from deteriorating too quickly under radiation. Its shelf life must match the duration of the mission, while the amount carried remains limited by transportation mass. An entire hospital cannot be brought along, so the medical inventory must be chosen according to the situations most likely to occur and the consequences if they cannot be treated. A serious injury could force the mission to end early, but returning home cannot happen within minutes. The crew must move the patient to the spacecraft, prepare for liftoff, rendezvous with Orion in orbit, and then begin the journey back to Earth. Even if everything is ready, the distance is still great enough that the base must be capable of caring for the patient while they wait. Radiation is another danger that, in most cases, produces no immediate sensation. On the lunar surface, humans are not protected by the thick atmosphere and global magnetic field that surround Earth. High-energy particles from deep space can pass through the body, while intense solar activity can sharply increase radiation levels over a short period. The longer people remain, the more carefully their total exposure must be managed. Outdoor activities must be scheduled according to space weather forecasts. When the sun is stable, the crew can carry out an excursion as planned. If monitoring instruments detect an eruption that may be directed toward the Moon, the astronauts may have to return early or postpone the activity entirely. There are no dark clouds or thunder to provide warning, only data from observatories and alerts appearing on a screen. The base needs a shelter with more shielding than the rest of the habitat. It may be positioned deep within the structure and surrounded by water, stored supplies, or a thicker layer of lunar soil. When a radiation warning appears, the crew brings food, water, and communication equipment into that small space and remains there until the danger has passed. An ordinary working day may suddenly contract into only a few square meters. During this confinement, the discomfort comes from more than the danger outside. Several people must remain close together in a cramped space without knowing exactly when they can return to work. The sound of fans, artificial light, and updates from Earth become their entire world. The event may end without causing harm, but the sense of vulnerability remains because the crew understands that the material surrounding them is replacing the atmosphere of an entire planet. Even when no emergency occurs, psychological well-being inside the base still requires attention. A small living space offers limited privacy. Each person works, eats, and rests beside the same crewmates for weeks at a time. A quiet sound, a repeated habit, or a difference in how work is organized may gradually become irritating when no one can visit a park, change rooms, or spend time with another group of people. A clear daily schedule can reduce some of that strain. The crew needs to know when to work, exercise, and rest. But the routine cannot be so rigid that every day feels exactly the same. Private time, calls with family, movies, music, or a small personal hobby can help each person preserve the feeling that they are still an individual, not merely one component within the base's systems. The distance from family is both near and far. Signals travel quickly enough for astronauts to hear familiar voices without waiting several minutes, as they would on a Mars mission, but they cannot touch their loved ones or return immediately if something happens. Earth may be clearly visible outside the window, close enough to appear as a blue sphere, yet still separated from them by a complicated journey through space. Seeing home without being able to return at once may feel different from living aboard a station in low Earth orbit. From the Moon, Earth does not spread across the view below. It hangs in the sky as a distant object. The oceans and continents cannot be seen in detail with the naked eye, but the blue color and white clouds are enough to remind the astronauts that everyone they have ever known is living on that small sphere. Sleep becomes an important part of the crew's ability to work. Near the South Pole, the light outside does not follow a familiar 24-hour cycle. The sun may remain close to the horizon for many days before an area enters a prolonged period of darkness. If humans relied only on natural light, their internal clocks could lose their rhythm, affecting mood, concentration, and health. The lighting system inside the habitat must create an artificial day. Bright light with the appropriate tone is used when the crew needs to remain alert, then gradually dims toward the end of the day. Temperature, meal times, and work schedules are also kept relatively stable so the body can recognize when it should be awake and when it should sleep. A lunar base must carry not only Earth's air, but also its sense of time. A sleeping compartment may be only large enough for one person to lie down and store a few personal belongings. Thin walls cannot completely block the sounds of machinery or the movement of crewmates. A sleeping astronaut may use earplugs, curtains, and personal lighting to create a sense of separation. Even in such a small space, a photograph, a book, or an object brought from home can make it feel more familiar. The ability to rest well directly affects safety. Sleep deprivation reduces reaction speed, memory, and accuracy in decision-making. In an environment where a valve closed incorrectly or a misplaced step can have serious consequences, fatigue is not merely uncomfortable, it becomes a technical hazard, much like a deteriorating component or a malfunctioning sensor. Mission commanders must therefore know when work should stop. A surface activity may be scientifically valuable, but extending it by another hour when the crew is already tired could increase the danger. A long-term presence is not measured by how many hours people can work without stopping. It is measured by their ability to repeat that work over many days while remaining physically and mentally healthy enough to continue. We still do not know how living for years under 1/6 of Earth's gravity would affect the human body. Exercise may slow the weakening of muscles and bones, but its long-term effectiveness has not been demonstrated in the lunar environment. Radiation exposure can be reduced through shielding, yet safe limits for many years of residence still require more data. Human psychology may also change across durations, longer than any mission ever attempted. Questions about permanent communities, children, or human development in low gravity lie even farther ahead. There is no direct evidence showing whether people could complete an entire healthy life cycle on the Moon. The first bases will therefore be temporary workplaces for carefully selected and closely monitored crews, not cities inhabited by multiple generations. At the end of the day, an astronaut records the condition of their body, reviews the schedule for tomorrow, and walks toward a small window. Outside, the gray surface lies still beneath low-angle sunlight. Dark shadows stretch across the craters, and the sky contains no blue. Farther away, Earth hangs in the darkness, bright and cloud-covered, like a world that is almost unreal. The astronaut watches that sphere for several minutes before the habitat lighting shifts into nighttime mode. Their body is still a body born on Earth, one that needs a 24-hour day, movement, rest, and a sense of connection with other people. The Moon challenges more than the machines that preserve air and water. It tests whether humans can carry the ordinary feeling of life into a place that is completely extraordinary. A crew may adapt for several weeks, learning how to walk, sleep, exercise, and work in low gravity. But for a base to survive for many years, humans must solve another problem. What happens when a pump stops, a robotic arm becomes stuck, or a filter needs replacement while the shipment carrying new parts is still on Earth? A person with a mass of 60 kilograms on Earth still has the same mass on the Moon, but their legs feel only a small fraction of the familiar weight. They can lift objects more easily, take longer steps, and leave the ground with only a gentle push. Yet that lightness raises a question that still has no complete answer. What happens when the human body spends months living under gravity only 1/6 as strong as Earth's? Morning at the base begins before the astronauts see the landscape outside. The lights inside the habitat gradually brighten according to a predetermined schedule, replacing a sunrise that does not occur with the same regularity as it does on Earth. Fans continue running through the ventilation system, while screens display temperature, pressure, and air quality. A new day is marked not by the rising sun, but by artificial light and a clock that helps the body preserve a familiar rhythm. An astronaut releases the straps, securing them to a sleeping bag or small bed, places their feet on the floor, and stands. Unlike the near-weightless environment of the International Space Station, the Moon still has gravity. The body still recognizes up and down, objects still fall to the floor, and a cup of water can still rest on a table. People can stand, walk, and work without gripping the walls to keep themselves from floating away. However, lunar gravity is only about 1/6 as strong as Earth's. An object with a mass of 60 kilograms is still difficult to accelerate or stop once it is moving, even though the person holding it feels far less weight. An astronaut may lift a cargo container more easily, but if they push it too forcefully, the container's mass can still pull their body along with it. The environment feels lighter, but that does not mean every activity becomes simple. When moving across the surface, humans do not walk exactly as they do on Earth. Apollo astronauts often shifted from ordinary steps to a gentle hopping or bouncing motion, because the stiffness of their suits and the low gravity made that style of movement more efficient. Each push could carry the body farther than expected, but when their boots touched down, loose dust and uneven terrain could still cause them to lose balance. Inside the base, the problem is less obvious but lasts much longer. On Earth, bones and muscles constantly work against gravity, even when a person is simply standing or walking across a room. With every movement, the leg muscles lift the body, the bones bear weight, and the heart pumps blood through a system shaped by millions of years of evolution under gravity. On the Moon, much of that load is greatly reduced. The clearest data available today comes from astronauts who have spent months in microgravity aboard the space station. When the body no longer has to support its own weight, less used muscles can weaken, especially those in the legs, back, and postural system. Bones may gradually lose minerals because they are no longer bearing the same loads. The cardiovascular system also changes as blood and other fluids are no longer pulled toward the lower body in the familiar way. But the Moon is not the same as a space station. 1/6 gravity may reduce some of these changes because people still have to stand, walk, and lift themselves from the ground. What remains unknown is how much protection that level of gravity provides for the bones, muscles, and cardiovascular system. No one has ever lived on the Moon for several months, so there is no direct evidence showing whether the body would stabilize or simply deteriorate more slowly. The answer can come only when humans begin staying for longer periods. The first cruise will be monitored very closely, from bone density and muscle strength to heart rate, blood pressure, and balance. Every mission extended by a few additional weeks will provide information that Earth-based simulations cannot fully replace. The human body will be both the instrument carrying out the mission and part of the larger experiment. To reduce the risk of physical decline, an astronaut's morning may begin with exercise. Ordinary weights would not provide the same resistance as they do on Earth, because a barbell would also weigh only 1/6 as much. Instead, exercise equipment may use springs, elastic bands, pistons, or other resistance systems to force the body to work. The astronaut must pull, push, and lift against forces created by the machine, rather than relying only on the weight of an object. A workout may combine movements for the legs, back, shoulders, and cardiovascular system. Astronauts may pedal a stationary cycle, pull handles, or perform motions that simulate lifting heavy loads. Restraints keep the body from bouncing away when force is applied. These exercises are not intended merely to preserve physical appearance. They prepare the crew for demanding work on the surface and for the eventual return to Earth. After months in low gravity, returning to a world with a stronger pull may become a challenge of its own. The leg muscles must once again support the body's full familiar weight. The cardiovascular system must adjust to keep blood flowing to the brain, while standing, and the sense of balance must adapt to the new environment. Someone may work effectively on the Moon, yet still feel heavy, dizzy, or weak after returning to Earth. Exercise is therefore also preparation for the journey home. After the workout, the astronaut checks several health indicators. An ordinary scale would not produce the same result as it does on Earth, because it measures the force with which the body presses against the floor. Other devices must be used to track mass, body composition, and muscle strength. Sensors may record heart rate, blood oxygen levels, and sleep quality, helping medical teams identify changes before they become serious problems. Breakfast takes place in a small area where the dining table may also serve as a desk and meeting space. Most of the food is still transported from Earth, then heated or rehydrated before being eaten. Under lunar gravity, crumbs fall onto the table instead of floating through the cabin, but they fall more slowly and may bounce away from the surface. Familiar actions remain, altered just enough to remind everyone that they are living on another world. After the meal, the crew reviews the day's plan. One group may prepare to go outside to inspect solar panels, collect samples, or repair equipment. The others remain inside to monitor the base, support communications, and prepare for the possibility that the excursion takes longer than expected. The schedule must balance scientific work, maintenance, exercise, meals, and rest, because an overloaded day can increase the risk of mistakes in an environment that offers few opportunities for correction. A lunar spacesuit turns every trip outside into a demanding physical activity. Although its weight is reduced, the suit still has considerable mass, its joints resist movement, and the wearer must constantly work against the pressure inside it. Bending down to retrieve a tool, turning the body, or walking uphill all require effort. Low gravity makes the astronaut lighter, but it does not eliminate the fatigue of spending hours working inside a sealed shell. When they return, astronauts must inspect their bodies just as carefully as they inspect their equipment. They look for signs of muscle pain, joint strain, dehydration, or discomfort caused by heat. A small scratch on Earth may be simple to treat, but on the Moon it must be monitored to prevent infection or interference with the ability to wear a spacesuit. Every change is recorded because a doctor cannot physically enter the base to examine them. Communication time between Earth and the Moon is far shorter than it would be with Mars. A conversation can still take place almost normally, even though the signal takes more than a second to travel in each direction. Doctors on Earth can review data, guide an ultrasound examination, or help assess a medical condition, but they cannot personally place a stitch, stabilize a broken bone, or move a patient onto an operating table. The crew must therefore be capable of handling many situations on their own. At least some members need enough medical training to assess injuries, administer medication, and perform basic procedures. Medical equipment must be small and lightweight, yet versatile enough to support everything from routine examinations to emergencies. A compact ultrasound device could replace several larger machines if the person using it receives proper guidance from Earth. Medication raises questions of its own. It must be stored at a stable temperature and protected from deteriorating too quickly under radiation. Its shelf life must match the length of the mission, while the quantity carried remains limited by transportation mass. An entire hospital cannot be brought along, so the medical inventory must be chosen according to the situations most likely to occur and the consequences if they cannot be treated. A serious injury could force the mission to end early, but returning home cannot happen within minutes. The crew must move the patient to the spacecraft, prepare for liftoff, rendezvous with Orion in orbit, and then begin the journey back to Earth. Even if everything is ready, the distance is still great enough that the base must be capable of caring for the patient while they wait. Radiation is another danger that, in most cases, produces no immediate sensation. On the lunar surface, humans are not protected by the thick atmosphere and global magnetic field that surround Earth. High-energy particles from deep space can pass through the body, while intense solar activity can sharply increase radiation levels over a short period. The longer people remain, the more carefully their total exposure must be managed. Outdoor activities must be scheduled according to space weather forecasts. When the sun is stable, the crew can carry out an excursion as planned. If monitoring instruments detect an eruption that may be directed toward the Moon, the astronauts may have to return early or postpone the activity entirely. There are no dark clouds or thunder to provide warning, only data from observatories and alerts appearing on a screen. The base needs a shelter with more shielding than the rest of the habitat. It may be positioned deep within the structure and surrounded by water, stored supplies, or a thicker layer of lunar soil. When a radiation warning appears, the crew brings food, water, and communication equipment into that small space and remains there until the danger has passed. An ordinary working day may suddenly contract into only a few square meters. During this confinement, the discomfort comes from more than the danger outside. Several people must remain close together in a cramped space without knowing exactly when they can return to work. The sound of fans, artificial light, and updates from Earth become their entire world. The event may end without causing harm, but the sense of vulnerability remains because the crew understands that the material surrounding them is replacing the atmosphere of an entire planet. Even when no emergency occurs, psychological well-being inside the base still requires attention. A small living space offers limited privacy. Each person works, eats, and rests beside the same crewmates for weeks at a time. A quiet sound, a repeated habit, or a difference in how work is organized may gradually become irritating when no one can visit a park, change rooms, or spend time with another group of people. A clear daily schedule can reduce some of that strain. The crew needs to know when to work, exercise, and rest. But the routine cannot be so rigid that every day feels exactly the same. Private time, calls with family, movies, music, or a small personal hobby can help each person preserve the feeling that they are still an individual, not merely one component within the base's systems. The distance from family is both near and far. Signals travel quickly enough for astronauts to hear familiar voices without waiting several minutes, as they would on a Mars mission. But they cannot touch their loved ones or return immediately if something happens. Earth may be clearly visible outside the window, close enough to appear as a blue sphere, yet still separated from them by a complicated journey through space. Seeing home without being able to return at once may feel different from living aboard a station in low Earth orbit. From the Moon, Earth does not spread across the view below. It hangs in the sky as a distant object. The oceans and continents cannot be seen in detail with the naked eye, but the blue color and white clouds are enough to remind the astronauts that everyone they have ever known is living on that small sphere. Sleep becomes an important part of the crew's ability to work. Near the South Pole, the light outside does not follow a familiar 24-hour cycle. The sun may remain close to the horizon for many days before an area enters a prolonged period of darkness. If humans relied only on natural light, their internal clocks could lose their rhythm, affecting mood, concentration, and health. The lighting system inside the habitat must create an artificial day. Bright light with the appropriate tone is used when the crew needs to remain alert, then gradually dims toward the end of the day. Temperature, meal times, and work schedules are also kept relatively stable, so the body can recognize when it should be awake and when it should sleep. A lunar base must carry not only Earth's air, but also its sense of time. A sleeping compartment may be only large enough for one person to lie down and store a few personal belongings. Thin walls cannot completely block the sounds of machinery or the movement of crewmates. A sleeping astronaut may use earplugs, curtains, and personal lighting to create a sense of separation. Even in such a small space, a photograph, a book, or an object brought from home can make it feel more familiar. The ability to rest well directly affects safety. Sleep deprivation reduces reaction speed, memory, and accuracy in decision-making. In an environment where a valve closed incorrectly or a misplaced step can have serious consequences, fatigue is not merely uncomfortable. It becomes a technical hazard, much like a deteriorating component or a malfunctioning sensor. Mission commanders must therefore know when work should stop. A surface activity may be scientifically valuable, but extending it by another hour when the crew is already tired could increase the danger. A long-term presence is not measured by how many hours people can work without stopping. It is measured by their ability to repeat that work over many days while remaining physically and mentally healthy enough to continue. We still do not know how living for years under 1/6 of Earth's gravity would affect the human body. Exercise may slow the weakening of muscles and bones, but its long-term effectiveness has not been demonstrated in the lunar environment. Radiation exposure can be reduced through shielding, yet safe limits for many years of residence still require more data. Human psychology may also change across durations longer than any mission ever attempted. Questions about permanent communities, children, or human development in low gravity lie even farther ahead. There is no direct evidence showing whether people could complete an entire healthy life cycle on the moon. The first bases will therefore be temporary workplaces for carefully selected and closely monitored crews, not cities inhabited by multiple generations. At the end of the day, an astronaut records the condition of their body, reviews the schedule for tomorrow, and walks toward a small window. Outside, the gray surface lies still beneath low-angle sunlight. Dark shadows stretch across the craters, and the sky contains no blue. Farther away, Earth hangs in the darkness, bright and cloud-covered, like a world that is almost unreal. The astronaut watches that sphere for several minutes before the habitat lighting shifts into nighttime mode. Their body is still a body born on Earth, one that needs a 24-hour day, movement, rest, and a sense of connection with other people. The moon challenges more than the machines that preserve air and water. It tests whether humans can carry the ordinary feeling of life into a place that is completely extraordinary. A crew may adapt for several weeks, learning how to walk, sleep, exercise, and work in low gravity. But for a base to survive for many years, humans must solve another problem. What happens when a pump stops, a robotic arm becomes stuck, or a filter needs replacement while the shipment carrying new parts is still on Earth? A small valve stops closing properly. On Earth, a technician could check the part number, order a replacement, and wait for a delivery truck to bring it. On the moon, that distance is nearly 400,000 kilometers. There is no store, no factory in the neighboring city, and no repair crew waiting outside the door. There is only what has already been delivered, what robots can reach, and what the crew can do for themselves. The failure does not begin with an explosion or a red warning echoing through the base. It appears only as a slowly changing pressure reading on a screen, showing that a valve inside a pipe no longer seals as tightly as it once did. The system continues operating. No air has been lost, and the crew is not yet in danger. But if the small leak continues, another device will have to work harder, and the reserves may gradually be depleted. The sensors are the first to recognize that something is wrong. They compare the current flow with data from previous days and detect a deviation too subtle for humans to notice through sound or smell. Diagnostic software begins examining possible causes, from an inaccurate sensor to dust blocking the valve or wear inside the mechanism. Rather than waiting for the equipment to fail completely, the base must learn to recognize early signs of decline while there is still time to respond. The crew redirects the airflow through another pipe and isolates the damaged section. This can be done safely only because the system was designed with multiple branches and backup components. If all the air depended on a single valve, a minor failure would immediately become a serious threat. A long-term base cannot allow one device to determine whether humans can continue breathing, drinking water, or maintaining a safe temperature. Once the affected section has been isolated, an astronaut opens the tool storage area and searches for the correct component. Every wrench, connector, and pressure seal must have been recorded before leaving Earth. Inside a small base, having enough equipment is not useful if no one knows which container holds it. A misplaced part could waste valuable hours while the backup system continues consuming electricity and other resources. Logistics on the moon begins with details this small. Food, filters, medicine, clothing, cables, and replacement parts all need clearly assigned locations and continuously updated service histories. The base must know how long each filter has been operating, which components have already been repaired, and how many months the remaining spares can support. Every object has not only mass, but also a future moment when it may become essential. On Earth, a technician can choose among many nearly identical parts. On the moon, a slight difference in size or connector type can make a component completely unusable. Standardization therefore becomes part of safety. If several machines use the same valves, filters, or fasteners, the crew can carry fewer spare parts while still being able to repair more systems. The same electrical connector might serve a rover, a scientific instrument, and a pump. Using one type of bolt in many locations reduces the number of tools that must be carried. These decisions receive little attention, while a base still exists only in drawings. Yet they determine whether a repair can be completed within a few hours or must wait for the next resupply mission. Simplicity in design can sometimes be more valuable than a highly specialized system. Not every component can be replaced with an identical locally made version. Precision sensors, electronic circuit boards, and heavy-duty bearings will still need to be manufactured on Earth during the early years. But simpler parts may be produced at the base using compact machine tools or three-dimensional printers. A handle, mounting bracket, protective cover, or section of low-pressure tubing could be created when needed. Three-dimensional printing would not turn the base into a factory capable of producing everything. The machine would still require raw materials, electricity, software, and time. Components exposed to pressure, high temperatures, or heavy loads must meet levels of precision that a small machine on the moon may not be able to provide. But the ability to produce a temporary part could keep a system operating until an official replacement arrives. To manufacture the correct component, the base must store engineering drawings and material data. Software could guide the crew through each step, showing which section must be removed and warning them about parts that remain pressurized or electrically active. An engineer on Earth may observe through a camera, but the person on the moon is the one holding the tools. The crew must understand the system well enough to recognize when the instructions do not fully match the actual situation. Robots could assist in areas that are difficult to reach. A robotic arm might inspect the outside of the habitat, hold equipment in place, or pass tools to an astronaut wearing a spacesuit. Smaller robots could move along the walls of the base, photograph joints, and search for temperature changes that might reveal a leak. Repetitive or dangerous work could be assigned to machines before a human has to step outside. But robots should not appear only after the base has already been built. They need to arrive before the crew, when the surface still has no roads, power network, or shelter. The earliest missions must survey the terrain, measure radiation, search for water ice, and examine lighting conditions. From that data, humans can begin identifying which regions are flat enough for landing, where solar panels should be placed, and which routes rovers can travel safely. A robot may cross the planned base site months before any human arrives. It records slopes, measures how deeply its wheels sink, and marks large rocks that should be avoided. As the lighting changes, it observes which areas fall into darkness and which continue receiving energy. These maps allow landing plans to be based on real surface conditions rather than orbital images alone. Robots could also deploy scientific instruments and radiation sensors at several locations. A small station operating for months could reveal how radiation levels change, how quickly dust accumulates on surfaces, and how many thermal cycles equipment can withstand. When the crew arrives, they will not be stepping into a completely unknown place. Machines will already have lived there long enough to reveal the first dangers. Cargo could also be delivered before humans. Habitats, reserve batteries, food, and rovers could be placed in selected areas, then inspected by robots. If a solar panel fails to unfold completely or an antenna shifts during landing, a robot may be able to correct it. The crew should not arrive only to discover that electricity and communication are not yet available. This makes robots the first builders of the base. They could pull cables, move cargo containers, and transport equipment from the landing zone to the place where it will be used. The work may proceed more slowly than construction on Earth, but it does not require humans to wear spacesuits and consume oxygen for many hours. Every task completed before the crew arrives reduces risk during the first days on the surface. The landing zone is one of the most important pieces of infrastructure that must be prepared. When a large lander descends, its engine exhaust can excavate the soil below and send dust and fragments of rock across great distances. If habitats, solar panels, or rovers are too close, those particles may strike their surfaces, scratch windows, and cover equipment in dust. An expanding base cannot allow every new cargo delivery to threaten everything that has already been built. The landing area must be far enough from the living quarters to protect them, yet close enough that moving cargo does not become a long journey. The route between the two locations must avoid steep slopes, extremely soft ground, and regions where communication may be lost. A rover carrying food or oxygen tanks cannot spend most of its energy crossing difficult terrain simply because the spacecraft landed in an inconvenient place. A reinforced surface could reduce the amount of soil disturbed by engine exhaust. On Earth, people can bring concrete, asphalt, and construction machinery to a work site. On the Moon, every kilogram transported from Earth is extremely expensive. Researchers are therefore studying ways to use lunar soil itself to create paving, bricks, or more stable surfaces. The soil could be compacted, heated, or processed through other methods that bind the particles together. A robot might treat one section at a time, gradually creating an area less vulnerable to erosion during landings. But this technology is not yet a construction system ready for large-scale deployment. The equipment must survive dust, consume substantial electricity, and process an area wide enough to provide meaningful protection. Turning lunar soil into bricks or structural components also offers possibilities for habitats and roads. Instead of transporting every protective wall from Earth, robots might create blocks of material to build around living modules or shield electrical cables. But soil properties vary from place to place, and the finished material must withstand temperature extremes, radiation, and impacts over long periods. A brick that performs well in a laboratory may not retain the same properties after years on the Moon. Three-dimensional printing with local material often appears in images of future lunar bases. A robotic arm moves around a habitat, placing layer after layer of processed soil to form a protective wall. The idea could reduce the amount of material that must be launched from Earth, but it still depends on electrical power, binding agents, precision, and the ability to repair the printer itself. The first bases may use this technology only on a small scale before attempting to build larger structures. While those construction methods continue to mature, robots can still perform the simpler task of moving soil. They may pilot around habitats, fill trenches that hold cables, or create protective berms facing the landing zone. The work does not require a perfect shape, yet it can still increase protection. A layer of soil placed in the right location may sometimes be more useful than a complicated wall that cannot yet be built reliably. All of these activities must be coordinated among vehicles created by different organizations. A lander built by one company must deliver cargo in sizes that a rover from another company can lift or tow. The electrical connector on one device must be compatible with the base's power network. Data from the robots must be readable by mission control software and shared with other systems. A cargo container is useless if a rover has no way to secure it. A solar panel cannot provide power if its connector is incompatible. A crewed spacecraft cannot become part of the base if its doors, airlocks, and spacesuits do not work together. Shared standards transform separate machines into a system whose parts can support one another. This becomes especially important as the base develops over many years. Equipment delivered during the first mission may eventually need to connect with vehicles that had not yet been designed at the time. If every generation uses a completely different standard, older infrastructure will quickly become useless. A long-term base must be able to expand without dismantling and replacing everything after every few flights. Communication also requires a shared language. A rover must report its position, remaining power, and equipment status in a form that both the base and relay satellites can understand. If every vehicle formats its data differently, people may waste valuable time converting information while an emergency is already unfolding. Unified standards allow information to travel from a sensor to a display without being misunderstood. Inside the control room, the crew may see the entire base as a network. Every rover, solar panel, communication station, and storage area appears on a map along with its current status. A device beginning to run hotter than normal can be marked before it stops working. A rover consuming power faster than expected can be ordered to return before its battery falls too low. This is how the base learns to repair problems before they fully develop. Instead of waiting for a pump to stop, the software notices that its electrical consumption is gradually increasing. Instead of waiting for a rover wheel to become trapped, the system detects greater slippage along a section of the route. Maintenance can then be scheduled while conditions are still favorable, when the crew has the necessary tools and the backup systems are not yet under heavy strain. Not every warning leads to a failure. A sensor may produce inaccurate data because of dust or temperature changes. The software must compare several sources of information before reaching a conclusion. If the system issues too many warnings, the The crew may lose confidence in it and overlook an important sign. If the warning comes too late, the opportunity for a simple repair may already have passed. Humans still make the final decisions in uncertain situations. Robots can inspect, measure, and present possible explanations, but the crew must consider the effect on the entire base. They may choose to shut down a scientific instrument to preserve power for repair equipment, or postpone a surface excursion because a rover requires maintenance. Long-term survival demands the ability to set priorities, not merely follow a schedule. Between crewed missions, the base may not become completely silent. Robots continue inspecting solar panels, keeping antennas correctly aligned, and monitoring temperatures inside the habitat. Some living systems are shut down or reduced to their lowest levels, but equipment protecting the structure remains active. The base becomes like a locked house waiting for its occupants to return, while continuing to preserve itself through dark and cold days. A long-term presence therefore does not necessarily mean humans must remain there continuously from the first day. The early phase may consist of stays lasting several days or weeks, separated by months without a crew. Robots maintain the infrastructure, collect data, and prepare for the next return. Each flight adds more equipment, expands the operating area, and extends the amount of time humans can remain. After many missions, the base begins to accumulate a history. One solar panel may have been installed during the first flight, a living module may have arrived several years later, and a new rover may replace an older vehicle whose wheels have worn down. Equipment from different generations operates together, like old and new buildings in a small town. The ability to maintain everything becomes more important than keeping every component in perfect condition. A community is not created only by the number of people present. It also forms when many systems learn to share electricity, data, tools, and space. A rover transports a replacement part for a generator, and that same generator recharges the rover at the end of the day. A storage facility serves both the habitat and the scientific station. Each part begins depending on the others, creating a network larger than any single machine. But that dependence also creates risk. If a central system fails, many devices may be affected at once. The base must therefore remain connected while preserving the ability to separate when necessary. A living module needs enough backup power to survive if the shared electrical grid is interrupted, while a rover must have an alternative way to navigate if a relay satellite temporarily stops working. Resupply missions will remain essential. Even if the base can manufacture some simple parts, most medicines, electronics, food, and precision components will still have to come from Earth. Launch frequency determines how many reserves must be stored. If only a few cargo flights arrive each year, the base must carry enough supplies for long intervals and for possible delays. A storm, rocket malfunction, or problem at a launch site on Earth could postpone a resupply mission for weeks. The lunar crew cannot treat a delivery date as a certainty. They must maintain reserves large enough to continue living if the schedule changes. This increases the amount of mass that must be transported at the beginning, but reduces the chance that a problem on Earth will become a crisis on the Moon. Transportation costs also directly influence how the base is built. A heavy but highly durable component may be better than several lighter parts that require frequent replacement. On the other hand, a system that is too complex may be difficult to repair even if it operates more efficiently. Every design must balance performance, durability, maintainability, and the number of spare parts that must be carried. No one knows exactly how autonomous robots will be during the early years. They may survey terrain, transport cargo, and perform many repetitive tasks, but unusual conditions can still create situations their software has never encountered. A wheel trapped between two rocks or a robotic arm failing to grip an object correctly may require intervention from an operator on Earth. Autonomy will gradually improve each time the systems encounter and learn from a new problem. Eventually, the small valve from the beginning of the chapter is removed. The crew discovers that a grain of dust has entered the contact surface, preventing the mechanism from sealing completely. The component is cleaned, the seal is inspected, and the valve is reinstalled. Airflow is restored step by step, while sensors monitor the pressure to make sure the leak does not return. There is no dramatic moment when the work is complete. There is only a reading returning to normal and the backup pipe becoming available for the next time it is needed. But this is what long-term survival on the moon truly looks like. The base does not survive because nothing ever breaks. It survives because failures are detected, problems are isolated, and repairs are made before one small malfunction spreads through the entire system. Months later, with no humans on the surface, a robot moves slowly around the base. It inspects connectors, clears dust from solar panels, and sends data to a relay satellite. Inside the habitat, the temperature is maintained at a low but safe level, while sensors continue listening for every change within the walls and pipes. Then a new signal arrives from orbit. The spacecraft carrying the next crew is approaching the moon. The robot leaves its charging station, travels toward the area outside the habitat, and activates systems that have been dormant for weeks. Guidance lights switch on one by one, antennas turn toward the sky, and electricity begins flowing once again through the living areas. Before humans arrive, the base has already awakened itself. It is no longer merely a room abandoned on the lunar dust, but a system capable of preserving power, inspecting equipment, and preparing for the next person to enter. At that point, the moon will no longer be only a place humans visit before leaving everything silent behind. But if an outpost can sustain itself between missions, use robots to prepare infrastructure, and help humans live farther from Earth for longer periods, a larger question begins to emerge. Will those lessons truly bring us closer to Mars? From the moon, Earth is only a few days away. From Mars, the journey home could take many months. A message sent from the moon takes just over a second to reach our home planet, while from Mars, the delay can stretch to many minutes depending on the positions of the two worlds. The moon is still far away, but compared with Mars, it is a place where humans can learn how to leave home without completely losing the path back. The journey began with a spacecraft flying around the moon and returning to Earth. Then two vehicles had to learn how to find each other in orbit, dock, and open an airtight passage through the vacuum. Next came the challenge of descending near the South Pole, where sunlight travels almost horizontally and no atmosphere exists to slow the fall. Each step has not only carried humans farther, but also revealed a new layer of difficulty. Once the spacecraft has touched down, the challenge is no longer simply reaching the surface. Humans must build a shelter that can keep air inside, prevent sharp dust from entering equipment, and protect the body from radiation. That room must maintain a safe temperature, detect leaks, and continue preserving life while only vacuum exists outside. A successful landing merely brings humans to the entrance of a much larger problem. Inside the habitat, every breath must be managed. Carbon dioxide must be removed, oxygen must be replenished, and moisture must be recovered before it collects on the walls. Used water must pass through purification systems and return to the cycle. Ordinary actions such as drinking, washing, or exercising all depend on a network of machines that cannot be allowed to stop. Outside the base, permanently shadowed craters preserve the hope of a local water supply. But the ice does not lie in clear underground lakes, waiting to be pumped out. It may be mixed with soil, buried at different depths, and present only in very low concentrations. To turn evidence of ice into a cup of water, humans must survey, drill, heat, capture vapor, purify it, and store it without allowing that precious resource to escape into the vacuum. Every stage of that process requires electricity. The base must endure long periods of darkness while keeping fans, pumps, heaters, and communication systems running. Solar power, batteries, fuel cells, and fission systems may all contribute, but no single option is guaranteed to solve every problem. Life will be preserved not by one perfect machine, but by many systems capable of supporting and replacing one another. Eventually, the human body itself becomes part of the test. Lunar gravity is not zero, but it is only about 1/6 as strong as Earth's. Muscles, bones, the cardiovascular system, and balance may all change when people live there for extended periods. Astronauts must exercise, maintain a stable sleep cycle, and learn to manage their health while the nearest hospital remains on another world. When equipment fails, the base must continue surviving with what is already available. Sensors must detect signs of deterioration before a component stops completely. The crew needs tools, spare parts, and the ability to manufacture certain simple items. Robots must inspect solar panels, pull cables, transport cargo, and prepare the base for the next human arrival. All of these abilities could become lessons for a journey to Mars. An interplanetary mission will also require more closed-loop life support systems, independent sources of power, robots working before humans arrive, and the ability to make repairs without waiting for a technical team to reach the site. A Mars crew will also have to manage water, air, food, and health in an unfamiliar environment. The Moon allows humans to begin practicing these skills at a much closer distance. That shorter distance does not make the lunar environment gentle. There is still no air outside the base, radiation still reaches the surface, and dust can still wear down critical joints. Temperatures change dramatically, shadowed regions can become extremely cold, and one small failure may still end a mission. The Moon is dangerous enough to challenge these systems, yet close enough to give humans a chance to return within a few days. That closeness provides a margin of safety Mars cannot offer. If an astronaut is seriously injured on the Moon, bringing them back to Earth would still be complicated, but the journey could be measured in days. On Mars, the two planets do not move into favorable positions on demand, and the return trip may take many months. An emergency would require more than immediate treatment. It could force the crew to provide ongoing care for a very long time. Communication also creates a major difference. From the Moon, a doctor on Earth can speak with the crew with only a brief delay. Operators can send instructions to a robot and receive a response within seconds. From Mars, every question and answer may be separated by many minutes, making direct control almost impossible. Humans and machines must make far more decisions on their own without waiting for permission from Earth. A lunar base could therefore become a place where autonomy is developed step by step. At first, teams on Earth may closely monitor nearly every activity. Later, robots can be given more responsibilities, while the crew handles common failures independently. Over time, the base may operate for longer periods without constant guidance, preparing for an environment where help from Earth will always arrive late. Life support systems can also be tested across several generations. A filter that operates for a few weeks can be replaced by a design capable of lasting for months. Water recycling loops can gradually recover a greater percentage, while the amount of consumable material decreases. Every stay on the Moon helps engineers learn which systems are truly durable, which components fail most often, and how many spare parts must be carried on a more distant journey. Robots can learn how to prepare a habitat before humans arrive. On the Moon, they may survey terrain, deploy cables, inspect power systems, and move cargo between the landing zone and the base. On Mars, similar work may need to be completed before the crew even leaves Earth, because no one wants to reach a distant planet only to discover that the habitat has no power or that the communication system failed to deploy properly. Using local resources is another important lesson. On the Moon, humans hope to turn ice into water, oxygen, and perhaps propellant. On Mars, the atmosphere contains carbon dioxide, while the soil may hold water in different forms. The technologies will not be exactly the same, but the underlying principle remains unchanged. A long-term outpost cannot continue bringing everything it needs from Earth forever. Independent power is another challenge shared by both the Moon and Mars. Solar energy may be used in both places, but the lighting conditions, dust, and duration of darkness are different. Fission power could provide a more stable supply for certain operations, though it would still need to be deployed and maintained safely. What humans learn from combining several energy sources on the Moon could help create a more flexible power grid for Mars. Dust is also present in both environments, but it is not the same. Lunar dust is sharp, dry, and highly adhesive because the surface has no water or wind to smooth its edges. Martian dust is carried by the wind, can spread across vast regions, and may form storms that reduce sunlight for long periods. A dust control system that succeeds on the Moon could provide valuable experience with seals, filters, and protective surfaces, but it would still need to be adapted for the Martian environment. Radiation creates a shared need for protective shelter as well. Neither the Moon nor Mars shields humans as effectively as Earth. However, Mars has a thin atmosphere, while the Moon has almost none. The types of radiation, the way they interact with the soil, and the amount of shielding required are not exactly the same. Data from one world can help with the other, but it cannot be applied without adjustment. The Moon is also not a smaller copy of Mars in terms of gravity. Martian gravity is stronger, a little more than 1/3 of Earth's, while lunar gravity is only about 1/6. The human body may respond differently in the two environments. If astronauts still lose significant bone and muscle on the Moon, that will not reveal exactly what would happen on Mars, but it will help researchers understand what to monitor and how to prepare. A day on Mars lasts nearly as long as a day on Earth, while the lunar cycle of light and darkness moves much more slowly. A Mars crew could build its daily routine around a day only slightly longer than 24 hours. On the Moon, especially near the poles, outside light may remain for long periods or disappear because of the terrain. Solutions for sleep and energy therefore cannot be transferred unchanged from one place to the other. Mars also has an atmosphere. Although it is very thin, it can create drag on a spacecraft, but not enough for a large vehicle to rely on parachutes alone during landing. Wind can move dust and affect equipment in ways that do not occur on the Moon. Temperature, pressure, and soil chemistry are also different, requiring each world to have its own vehicles, spacesuits, and habitats. Success on the Moon will therefore not automatically guarantee success on Mars. A lunar base may prove that a water recycling system can operate more reliably, but a journey to Mars must also endure many months in deep space. Robots may work well with short communication delays on the Moon, but on Mars they will need much greater autonomy. Every lesson will be useful, yet each one will remain only part of a larger challenge. The value of the Moon lies in the opportunity to repeat. A mission that encounters difficulties can be adjusted for the next flight within a shorter period. New equipment can be sent without waiting years for another interplanetary launch window. Crews can return, describe what they experienced, and help the people who follow prepare more effectively. NASA refers to this approach as the Moon to Mars architecture. The goal is not to make every lunar mission an exact copy of a future Mars expedition, but to develop shared capabilities through a series of stages: rendezvous in space, precise landing, life support, surface power, robotics, logistics, and medical care can all be tested at a closer distance before humans commit themselves to a journey from which returning will not be easy. But even on the Moon, the word living must be understood carefully. A crew staying for several days does not create a long-term base. A habitat operating for a few weeks will still depend almost entirely on supplies brought from Earth. A sustainable presence does not appear in a single moment. It is built through several different levels. The first level is visiting, like the Apollo missions, when humans arrive, complete their work, and return home. The next is remaining longer, long enough to experience many working days and test systems under changing conditions. After that, missions may return more frequently and reuse part of the infrastructure left behind. The Moon then begins to have a place to which humans return, rather than forcing every mission to begin again from nothing. A further step would allow robots to maintain the base between missions. They could keep solar panels clean, inspect cables, monitor leaks, and prepare the habitat before the crew arrives. Humans would not yet be present continuously, but the outpost would no longer be completely abandoned. It would continue operating at a reduced level, waiting and protecting the equipment accumulated across many missions. Only after that might humans begin remaining almost continuously. As one crew prepares to return home, the next may already be on its way or scheduled to arrive after only a short interval. The base would need enough living space, electricity, water, food, and repair capacity to prevent crew rotations from creating dangerous gaps. This stage would require far more launches and a much more dependable logistical chain. The level of independence could also increase gradually. At first, all drinking water and reserve oxygen would be transported from Earth. Later, the base might produce some oxygen, recover most of its water, and experiment with processing small amounts of local ice. Simple materials could be made from lunar soil, while precision components would still need to arrive from the home planet. The coming decade may achieve some of these steps, but not necessarily all of them. Humans may return to the surface, remain longer, and begin using habitats and rovers delivered in advance. Robots may maintain equipment between missions, But that would not mean a city had appeared or that hundreds of people were living permanently beyond Earth. Milestones such as 2030 or 2032 should be understood as directional goals rather than guaranteed completion dates. Progress will depend on landers, rockets, funding, test results, and cooperation among many partners. A technical failure could alter the schedule, while a new discovery about ice or terrain could lead planners to reconsider the location of the base. Funding will also determine how quickly the outpost can expand. A base requires many launches carrying habitats, power systems, rovers, food, and spare parts. If flights do not occur frequently enough, the gaps between missions will grow and larger reserves will be required. A long-term presence is not only a scientific challenge, but also the challenge of sustaining a program through many years and changes in policy. The final architecture for Mars has not yet been fully defined. It remains uncertain which spacecraft the crew will live in, what kind of propulsion they will use, and how long they will remain on the surface. The Moon cannot answer every one of those questions, but it can help eliminate systems that are not durable enough and clarify the capabilities humans must develop before traveling farther. Imagine the final day of a lunar mission. The crew completes an inspection of the habitat, seals the sample containers, and loads the last tools onto the rover. They reduce the activity of the living systems, place the base into standby mode, and pass through the airlock. The door closes behind them, preserving the remaining atmosphere inside a room that will remain unoccupied for several weeks. Outside, they board the lander and begin leaving the Moon. The engines lift the vehicle above the dust and carry it toward the orbit where Orion is waiting. Through the window, the base becomes smaller, reduced to a few bright shapes among the gray terrain. There is no crowd to see them off, only robots and equipment continuing to operate below. After the spacecraft departs, a rover returns to the habitat. It inspects the solar panels, examines the connectors, and stops at its charging station. Inside the base, the fans no longer run at the level required for human occupants, but sensors continue monitoring pressure and temperature. A few guidance lights remain illuminated, enough for cameras to recognize the paths surrounding the habitat. Above the horizon, Earth still hangs in the darkness. On that blue sphere, the crew is beginning its journey home, while millions of people may be watching data from the instruments left behind. The Moon is once again without humans, but it is no longer completely silent in the way it once was. A small piece of Earth's infrastructure continues operating on its surface. The first sign that humans are beginning to live on the Moon may not be a giant dome or a new flag. It may simply be a room that continues holding pressure when no one is inside, a robot that checks the power supply on its own, and an antenna that remains pointed toward Earth. Those systems will wait for the next crew, not as abandoned objects, but as a place preparing to welcome people back. Humanity may not build a city on the Moon within the next decade, but if one room can preserve its air, one system can recycle water, one robot can work without human presence, and one power source can remain active through the darkness, then, for the first time in history, life from Earth will no longer merely visit another world.